Hello there and welcome to Science for Sleep, where curiosity is allowed to stretch out comfortably, and science takes its time to wander gently through the questions that make our universe feel both astonishing and strangely comforting. Tonight we're going to sink slowly into a question that people have been whispering to themselves since the first eyes turned upward into the dark sky. What is the actual size of the universe? It sounds simple when you first hear it, like asking how tall a mountain is or how long a river might flow. But the more you lean into it, the more the question begins to expand in every direction, a little like the universe itself. We live inside something so vast that even finding the edges of the question becomes its own adventure. I wonder where you are listening from right now. Perhaps you're lying in bed, perhaps you have a nightlight on the side table, or the gentle glow of a phone screen still nearby. Maybe the window is cracked open and the sound of the outside world is softer than usual, a few faint noises drifting in while you listen. Or maybe you're somewhere far away from all of that, a quiet corner just for yourself, letting words fill the silence. Do you know what the night sky looks like above you right now? Is it clouded over, city lights hiding the stars, or are you somewhere you can see them clearly, little points scattered without any obvious end? That's really the beginning of this whole journey, looking up and realizing there's more than we can count, and then wondering if we could ever measure it all. Before we drift too far, let me say, if you find these slow explorations soothing, if you enjoy the calm of science stretched out like this, it would mean a great deal if you tapped like or subscribed. It helps others find this same calm space when they might need a soft moment in their day. That way, more people can share this gentle kind of curiosity, and you'll always have new quiet voyages waiting whenever you want them. So, settle yourself, let your shoulders sink, allow your thoughts to untangle a little as we step together into this question. The size of the universe. What does it even mean to ask that? Are we speaking about what we can see, or what might exist beyond? Do we mean the physical distances between things, or the invisible horizon beyond which no light has ever reached us? Do we mean the present, or the past, or the future? It's not as straightforward as measuring a room or even counting the miles across an ocean. Instead, it's something much stranger, something that bends the very ideas of scale, distance, and even time itself. Imagine for a moment the earliest people who looked at the stars. They didn't have telescopes or satellites. They had only their eyes, their patience, and their imaginations. For them, the question of size wasn't really about numbers. It was about feelings. The sky felt endless because it reached farther than sight. They saw the moon rise and set, the sun travel across the day, the stars shift with the seasons, and they placed all of that into stories. The size of the universe wasn't measured then, it was told, sung, passed down in myths that carried awe in place of mathematics. For some, the sky was a dome. For others, a great blanket pierced with holes of light. For many, it was the home of gods, ancestors, or mysterious forces. And yet, even then, behind those stories, the quiet human question remained. How big is all of this, really? When you think about that question today, sitting here in the modern world with lights, engines, and screens all around us, the wonder is still the same. We have more tools now, numbers that can climb into the trillions, telescopes that can see galaxies as smudges of light from billions of years ago. But even with all of that, the question resists a neat answer. Because every time we think we've found a measurement, we realize there's more. The universe doesn't end where our eyes or even our machines stop. It stretches farther, and then farther again, and the act of trying to pin it down becomes part of the experience itself. Think about the word size in this context. When you measure a room, you can walk across it with a tape measure. When you measure a continent, you can map coastlines, mountains, and rivers. When you measure the Earth, you can wrap satellites around it, bouncing signals back and forth until the numbers make sense. But with the universe, the measuring tape itself becomes part of the question. Light takes time to travel. The further away something is, the older the image we're seeing. Look at the moon, and you're seeing it as it was just over a second ago. Look at the sun and you're seeing it as it was about 8 minutes ago. Look at the nearest stars and you're seeing them as they were years ago. Look at galaxies and you're looking millions or billions of years into the past. So when we ask, what is the size of the universe, we aren't just asking about space, we're asking about time, memory, and the limits of observation. There's a comfort in this, strange as it may sound. The universe is too vast to be grasped all at once, so we take it step by step. We start small with what we can touch, the ground beneath us, the curve of the Earth, the orbits of the planets. Then we stretch outward, each layer of distance revealing something new. This is how science often works, a slow, careful expansion, one horizon at a time. It doesn't make the immensity less overwhelming, but it gives us handholds, little places to pause along the way. And that's exactly what we'll do here. We'll wander slowly, beginning with the familiar and moving outward, always outward, until the numbers bend under their own weight and the words struggle to keep up with what they're describing. We'll linger on the methods people used to measure, the tools that allowed them to see farther, the ideas that stretched minds before they stretched space. We'll talk about stars and galaxies, about the edges of the observable universe, about the possibility that there is no true edge at all. We'll consider the difference between what we can see and what we suspect might be, and what it means for us, tiny beings asking oversized questions from our little planet. If you've ever stared at the night sky and felt both incredibly small and somehow comforted by that smallness, then you already know the heart of this journey. That paradox of being insignificant in scale, but significant in thought, is part of what makes us human. The universe may be unimaginably large, but so is our capacity to wonder about it, to map it, to try, in our gentle way, to understand where we fit. And that, perhaps, is the true measure we're reaching for when we ask about size. When you look up at the night sky, it's easy to feel the first stirrings of the question without even putting it into words. You tilt your head back, the air is cooler, and above you there is that broad dome filled with scattered points of light. Some look bright, some faint, some steady, others flicker in a way that feels alive, and something in you begins to wonder, how far away are those lights? How many are there? Where does it all stop? This is the beginning of curiosity about the size of the universe. It doesn't start with equations or telescopes. It begins in silence, with the human eye meeting the unknown and asking a very natural, almost childlike question. How big is this really? The question is deceptively simple. It feels like it should have an answer waiting, like measuring a room or asking how long a road stretches. But with the universe, the more you look, the more the edges recede. Early people didn't have numbers large enough to carry the weight of the distances they were imagining, but they asked anyway. They stared at the horizon and then at the sky above it, comparing the two. They saw the way the stars shifted with the seasons, how different constellations rose at different times of the year, and they recognized that they were standing beneath something far larger than the ground they could walk across. Without needing instruments, they knew they were small. Think about what it must have been like for someone thousands of years ago standing under a clear night sky without city lights, without airplanes, without anything at all between them and the deep velvet darkness. It would have been overwhelming, almost too much to process. That feeling, though, is universal across time. Even now, with all our knowledge and all our technology, stand under a truly dark sky. One of those rare places where the Milky Way is visible as a river of faint light stretching from horizon to horizon, and the same thought arises. How big can this be? What makes the question fascinating is that it doesn't have to be about numbers. At its heart, it's about perception. When you see a star, your brain wants to assign it a place, a distance, a size. But stars don't give that away easily. They appear as points no matter how far they are. The brightest one in the sky might be relatively close, or it might be a giant burning so far away that its size tricks the eye into thinking it's near. Without tools, without some way to measure, the human mind fills in the blanks with imagination. Sometimes the sky was seen as a ceiling, low enough that gods or spirits could step down. Sometimes it was imagined as a great sphere surrounding the earth, with the lights fixed onto it like lanterns. Sometimes it was thought of as layers, a series of heavens stacked one above the other. In every version, the attempt was the same, to take an incomprehensible vastness and wrap it in a picture that the mind could carry. Even today, when we know that those stars are suns in their own right, light years away, the same instinct plays out. You can't really imagine a light year in your head. You can say the number, about 9.5 trillion kilometers, but the scale is beyond anything you can compare with your daily life. So the brain does something else. It imagines, not in kilometers or miles, but in feelings. Vast, endless, out there. The real measurements come later, but the feeling is the first step. That feeling is the first wonder. There's also something humbling about it. Looking up at the sky doesn't just make you wonder about size, it makes you aware of your own. Standing on the ground, you feel small but connected. You can't reach the stars, but you're part of the same universe that holds them. This isn't just poetic musing, it's the reality of being a tiny observer inside a cosmos you can't map in your head. The very act of asking how big puts you into relationship with the universe. You may not know the answer, but you know there is an answer out there, waiting. Different cultures throughout history answered the question in different ways. Some said the sky was infinite, others said it was a solid dome, others still believed it was a series of concentric spheres turning around the Earth. What's important is that the question never disappeared. From the moment people could look up and stay awake at night long enough to notice the movement of stars, they were already engaging with the first wonder of size. And there's something else, something subtle. When you ask, how big? You're also asking, where am I in all of this? That's why the question feels so compelling. It isn't just a matter of curiosity about distances. It's a way of locating yourself in the grand structure. If the universe is small, maybe your place is large. If the universe is infinite, maybe your place is tiny. The tension between those two possibilities is what drives the imagination forward. As time went on, people tried to answer more concretely. They watched how stars rose in one part of the world and set in another. They measured the lengths of shadows. They tried to calculate the size of the Earth itself, because they knew that if they could measure the ground beneath them, it might give them a clue about the heavens above. But before the tools and before the calculations, it was simply wonder. Children lying on their backs staring at the stars, storytellers weaving constellations into myths, travellers using the sky to find their way across seas. Wonder first, numbers later. That wonder is still with us. Even as astronomers now use sophisticated telescopes to capture galaxies, billions of light years away, the same basic question drives them. How big is it? They know the numbers, but they also know that behind every number is another layer of vastness, another mystery. It never ends, and that's part of why the question stays alive. If we ever reached a final answer, the story might feel finished, but the universe keeps stretching, literally expanding, and so the question continues to grow. When you stand under the night sky, you're participating in something ancient. Every human being who has ever looked up has had the same thought cross their mind. And even though the answers have changed from myths to models to mathematics, the first wonder has not. The feeling of scale, the sense of immensity, the unshakable awareness that you're standing on a small planet looking into something too big to fully know, that feeling is as old as humanity itself. And so, when you ask, how big? What you're really doing is joining that long line of questioners. You're stepping into the same stream of thought that carried people from campfires to observatories, from drawing star maps to building spacecraft. The first wonder is still the most important, because without it, none of the later answers would have been sought. Without looking up and asking how big, we would never have built the tools, we would never have made the measurements, we would never have stretched our minds to hold the idea of billions of galaxies. The universe doesn't answer back directly. It doesn't tell you its size in words or show you its edges. It just shines, quietly, waiting for you to notice. The act of asking is already the beginning of an answer, because it opens you to the reality that you're part of something larger, and as we continue outward, step by step, that question will stay with us. Not solved, not finished, just gently guiding us into the vastness. When you begin to ask how big the universe might be, the most natural place to start is with what we know best, the ground beneath our feet. Before we can stretch outward into light years and galaxies, it helps to understand the scale of the Earth itself, the place we call home. We live on this planet every single day, walking across its surface, flying through its skies, sailing across its oceans, but rarely do we pause to really think about its size in a way that connects to the larger question of the universe. To us, the Earth feels enormous. Roads stretch for hours, flights take many hours more, and oceans seem endless when you look out across them. Yet in cosmic terms, the Earth is both huge and incredibly small. It's large enough to contain everything we've ever known, but tiny compared to what surrounds it. Consider what it means to be standing on a sphere, a ball of rock and water suspended in space. Most of the time, we forget that. The ground feels flat, the horizon feels like a line, and everything seems stable beneath us. But in reality, we're on the surface of a globe, one that is turning steadily and orbiting a star at tremendous speed. The numbers are staggering once you say them aloud. The Earth has a diameter of about 12,142 kilometers. If you wanted to walk around the equator, it would take you more than 40,000 kilometers of steps. That alone feels beyond human scale, because no one person could ever realistically walk every inch of it. And yet, when compared to what comes later in the universe, that number shrinks into near invisibility. For ancient people, one of the great achievements was simply realizing that the Earth was round. To them, it felt flat because that was how it appeared from a human perspective. You look across a field or across the sea and the surface doesn't curve noticeably. But with patience and careful observation, the truth revealed itself. Ships disappeared bottom first over the horizon. The shadow of the Earth during a lunar eclipse was round. Travellers could move far enough to see different stars in the sky. All of these small clues added up to the realization that the Earth wasn't a flat surface, but a sphere. Once that was understood, the question of its size naturally followed. One of the most elegant answers came more than 2,000 years ago from a man named Eratosthenes, a Greek scholar living in Egypt. He noticed that on the summer solstice, in the city of Syene, the sun was directly overhead at noon. It shone straight down a well without casting a shadow. But in Alexandria, farther north, the sun cast a noticeable shadow at the same time. By measuring the angle of that shadow and knowing the distance between the two cities, he was able to calculate the circumference of the Earth with astonishing accuracy. Without satellites, without airplanes, without leaving the ground, he used nothing more than shadows, geometry, and curiosity to measure the size of the planet. His estimate was within a small percentage of the true value, a remarkable achievement that showed how powerful human reasoning could be. Think about what that means. Thousands of years ago, someone stood in the sunlight, looked at the length of a shadow, and from that simple observation, reached a number that told him the size of the entire planet. That's the same kind of curiosity that drives us to ask about the size of the universe today. We start with what we can see. We ask how it connects to something larger, and we follow the question outward until the answers come. For us today, the numbers are clearer. The Earth's circumference around the equator is just over 40,000 kilometers. Its surface area is about 510 million square kilometers, of which about 71% is covered in water. That means the oceans themselves are a kind of boundary, making the Earth feel even more vast to anyone who tries to cross them. In the past, oceans were seen as endless barriers, places where the known world seemed to end. But now we know they're part of a much larger whole, a skin of water wrapped around a sphere in space. Still, when you stand in one place, it's difficult to feel that. If you stand on a beach and look out, the horizon feels like the edge of everything. If you climb a mountain, you might see further, but still the curve is too gradual to notice. Only from space do we really see the truth. Photographs taken from orbit, the famous blue marble images, reveal the Earth in its fullness. From that distance, the size feels different. It's not infinite anymore. It's round, bounded, beautiful, and fragile. Astronauts often speak about this experience, how seeing the Earth from space changes their perspective. They call it the overview effect, a shift in awareness that comes from realizing the planet is both enormous and incredibly delicate at the same time. But let's keep the numbers in mind because they help anchor the imagination. 12,000 kilometers across, 40,000 kilometers around. Oceans that stretch thousands of kilometers in width. Mountains that rise nearly 9 kilometers high. Valleys that plunge even deeper below sea level. To us, those are huge. They dominate our lives, shape our maps, and define our journeys. And yet, compared to the Sun, the Earth is tiny. Compared to the solar system, it's a speck. Compared to the galaxy, it's invisible. That contrast is important because it shows us how scale shifts as we move outward. What feels enormous here becomes almost nothing in the larger frame. Imagine shrinking the universe into a model where the Sun is the size of a beach ball. On that scale, the Earth would be about the size of a small marble, orbiting about 2.5 meters away. Suddenly the Earth feels tiny, easy to miss, fragile, and yet that marble holds everything. Every mountain, every ocean, every city, every person who has ever lived, all contained in that one small sphere. It's humbling to think about. The place that feels infinite to us is just a dot in the cosmic scale. This perspective also helps us appreciate the idea of relative size. The Earth is huge when compared to us as individuals. It takes days to cross countries, weeks to sail oceans, and months to circle the globe in early times. But when compared to stars, galaxies, and beyond, it's almost nothing. That duality is at the heart of the cosmic question. We're always caught between feeling large in one context and small in another. It's not about one answer being correct and the other being wrong. Both are true, depending on where you stand. The Earth's size also plays a role in making life possible. Its diameter, its mass, its gravity. All of these are finely balanced to create conditions where an atmosphere can cling to the surface, where water can stay liquid, where temperatures can remain stable enough to support living things. Too small, and the atmosphere would leak away. Too large, and gravity would crush or trap gases in ways that make life difficult. So the Earth's size is not just a number, it's part of the reason we're here at all. That makes the question of scale more personal. It's not just about how big the planet is, it's about how its size shapes the possibility of us existing. When we ask about the size of the universe, we're also indirectly asking about the size of our home within it, and knowing the Earth's scale helps us make sense of what comes next. If Earth is 12,000 kilometers across, and the Moon is nearly 400,000 kilometers away, then suddenly the Earth's size feels like a unit of measure, a starting point to compare distances beyond. We take the familiar and use it as a ruler to measure the unfamiliar. That's how science moves forward, one comparison at a time. It's worth pausing on what it means to think of Earth as both everything and almost nothing. To us, it holds our entire history, every story, every discovery, every life. Yet in the photographs taken from deep space, Earth is a pale blue dot, as Carl Sagan described it, suspended in a sunbeam, barely visible against the blackness. The same object can be infinite in meaning and tiny in appearance, depending on how far away you stand. That dual nature of scale is what makes the exploration of size so endlessly fascinating. And so, when we talk about our cosmic backyard, we're not just placing Earth in numbers, we're placing it in perspective. It is the beginning of the journey outward. It is the first stepping stone beyond personal experience and into cosmic thought. From here, the numbers will grow, the distances will multiply, and the scales will stretch in ways that challenge our imaginations. But Earth remains the anchor, the place we start, the ruler we use, the home we compare everything else to. It's both ordinary and extraordinary, both vast and tiny, both the whole world and just one small part of something larger. Once people had learned that the Earth itself could be measured, that shadows and geometry could reveal its true size, the next step was almost inevitable. If the ground beneath us could be grasped with numbers, then perhaps the sky above could be too. The stars no longer had to remain only in the realm of myth and imagination. They could be studied, mapped, and maybe even measured. Of course, the distances involved were so much greater than anything on Earth that progress was slow, sometimes hesitant, sometimes full of mistakes. Yet those early attempts were the beginning of astronomy as a science, the first real moves toward understanding just how immense the universe truly is. Imagine standing in a world without modern technology, with no telescopes, no satellites, no precise clocks. You have only your eyes, your patience, and the willingness to watch the sky night after night. That is what ancient astronomers had to work with, and what they noticed was extraordinary. The stars didn't simply scatter randomly. They rose in the east, set in the west, and moved in patterns that repeated with the seasons. Some constellations were visible only in certain months. Others never disappeared from the sky. These patterns gave the first clue that the heavens were not just decoration, but a system, something that could be studied. The Babylonians, for example, kept careful records of the stars and planets as early as 2,000 years before our era. They observed the movements of Jupiter, Venus, and Mars, noting when they appeared and disappeared, how they shifted against the background stars. To them, these observations were tied to omens and predictions, but in practice they were building a foundation of astronomical data. By mapping the sky, they were taking the first step toward measuring its immensity. In Greece, thinkers like Hipparchus began to push the idea further. He created one of the earliest known star catalogues, carefully recording the positions of hundreds of stars. He also noticed something subtle. The position of the stars shifted slowly over time, a motion we now call precession, caused by the Earth's axis wobbling like a spinning top. To notice something like that required not just watching the sky once, but comparing observations across years and decades. This kind of patience was essential to the attempt to measure the heavens. But how do you measure something when you can't reach it? The moon was close enough to seem possible. Ancient astronomers could see it clearly, track its phases, and even notice how its size changed slightly depending on where it was in its orbit. By comparing the apparent size of the moon to the size of the Earth's shadow during a lunar eclipse, some were able to estimate the moon's distance. These weren't precise by modern standards, but they showed that the heavens could yield numbers, not just myths. The sun, too, became a focus of measurement. Its path across the sky marked the seasons, and by studying the length of shadows at different times of year, astronomers could not only keep track of calendars, but begin to understand the scale of Earth's orbit. In some cases, these measurements were astonishingly close to the truth, given the limited tools available. Of course, mistakes were common. Many ancient models placed Earth at the centre of the universe, with the sun, moon, planets, and stars moving around it. This made sense from a human perspective. After all, the ground feels unmoving, while everything else seems to circle us. But even within this framework, astronomers refined their measurements. They built intricate models of planetary motion, like the system of epicycles developed by Ptolemy to explain why planets sometimes appeared to move backward in the sky. These models were complicated and not entirely accurate, but they represented genuine attempts to match mathematics to observation. The sky was no longer an endless mystery. It was something that could be charted. Elsewhere in the world, other cultures were also measuring. Chinese astronomers kept records of eclipses and comets for thousands of years, building a continuous history of the sky. Mayan astronomers created calendars of remarkable accuracy by tracking the cycles of the Sun, Moon, and Venus. In India, scholars developed sophisticated mathematical techniques to predict planetary motion. All of these traditions shared the same impulse, to look up and ask not only what the sky meant but how it worked, and how far it might stretch. One of the great challenges was distance. The stars looked like points of light. Were they close and small, or far and enormous? Without the ability to measure parallax and the tiny shift in a star's position as Earth moves around the Sun, it was nearly impossible to say. So for a long time, many believed the stars were fixed to a sphere surrounding Earth. Not infinitely far, but at a distance just beyond the planets. That sphere of stars was thought to rotate daily, carrying everything with it. It wasn't accurate, but it was an attempt to give the sky a structure, to define its size in a way the human mind could manage. Consider the courage of those who tried to go beyond this. Aristarchus of Samos, a Greek thinker who lived in the 3rd century BCE, proposed something radical. He suggested that the Sun, not Earth, was at the centre, and the Earth moved around it. He also tried to estimate the relative distances of the Sun and the Moon. By comparing the angle between them during certain phases of the Moon, he concluded that the Sun must be much farther away than the Moon, and therefore much larger. His numbers were off by a wide margin, but the principle was revolutionary. He was among the first to suggest that the universe might be far larger than people had imagined. Imagine what it must have felt like to propose such an idea in a world that assumed Earth was the centre of everything. To say not only that Earth moved, but that the Sun was vastly larger and farther away, was to stretch the boundaries of human imagination. Even if the exact numbers were wrong, the attempt itself pushed thought outward, toward a universe of greater size. Instruments slowly improved the process. Simple tools like the gnomon, a stick casting a shadow, helped measure the Sun's position. The astrolabe allowed observers to measure the altitude of stars and planets with greater accuracy. Large observatories, like those built in ancient Persia and later in Samarkand, provided places where astronomers could gather data systematically. Each new tool made the sky a little less distant, a little more measurable. But for all their progress, the immensity of the sky remained out of reach. The stars gave no clue to their distances. They twinkled, but they did not reveal how far away they were. For centuries, this remained the great unanswered question. People could measure the Earth, the Moon, even make rough estimates of the Sun, but the stars defied measurement. They were simply too far. And that, in its own way, was part of the immensity. To look up and realize that no matter how clever your methods, the stars were still beyond reach, was to confront the true scale of the universe. This was not discouraging. If anything, it deepened the sense of wonder. The sky was measurable in some ways, but not in others. There were things we could know and things we could not, and the boundary between them shifted slowly as methods improved. That shifting boundary is what carried humanity forward. Every time someone found a new way to measure, the universe became larger, not smaller. Each discovery pushed the edge of immensity outward. What's striking is how much patience it required. Unlike experiments in a laboratory, astronomy demanded time. The stars moved slowly. The planets traced long loops across the sky. Eclipses were rare. To gather enough information to make sense of it all, observers had to watch for years, sometimes lifetimes. Knowledge accumulated across generations. One person might notice a detail, another might record it, another might compare it with something else, and together, over centuries, the picture grew clearer. Measuring the sky was not the work of one person or one culture. It was a human endeavour stretched across time, a slow unfolding of curiosity. And with each step, the idea of immensity became more real. The Earth was vast but finite. The Moon and Sun were farther than expected. The stars, though still mysterious, hinted at distances beyond comprehension. The attempts to grasp it all showed that the universe was not small, not bounded by the imagination alone, but something that stretched farther than anyone could yet say. That realization, more than any particular number, was the true achievement of those early astronomers. The sky could be measured, at least in part. It could be mapped, catalogued, and studied. And though the ultimate immensity remained beyond reach, the act of trying brought humanity closer to understanding its place. The numbers would grow more precise in time, the distances would eventually be calculated, the stars would give up their secrets. But it all began with those first attempts. The patient watching, the careful recording, the belief that even the heavens could be understood. And so, as we continue outward in our own exploration, we carry that legacy. The sky above us has always been immense, but through the eyes of those who measured before us, it becomes not just overwhelming but approachable. Each attempt, whether right or wrong, brought us a little closer to grasping the scale of the universe. The immensity remains, but so does the human determination to measure it step by step across generations. If the size of Earth was the first step in grounding our sense of place, then the moon was the natural next step outward. It is the most familiar object in the night sky, bright enough to command attention, close enough to show detail with the naked eye, yet distant enough to inspire the question, how far is it really? For countless generations, the moon was both companion and mystery. It guided tides, lit the darkness, marked the months, and stirred stories in every culture. But beneath all of that, quietly, people wondered, what is its true distance? And could we ever measure it? From the ground, the moon looks deceptively close. It rises with a comforting familiarity, changing its shape night by night, slipping through its phases with a rhythm so steady that it feels almost personal. Because it's large and bright, it feels nearer than the stars, nearer even than the sun, and in a sense it is. Yet once you try to put a number to that nearness, you realize just how far away it actually is. Today we know the average distance is about 384,400 kilometers. That's nearly 30 Earth diameters lined up in a row. To put it differently, if you could drive there at highway speed without stopping, it would take more than 5 months of continuous driving. For something that looks so close, it is astonishingly far. The attempt to measure it began very early. Ancient astronomers noticed how the moon interacted with the Earth and the Sun, and from those interactions they tried to infer its distance. One of the simplest methods came from observing lunar eclipses. When Earth passes between the Sun and the Moon, its shadow falls across the lunar surface. By watching the size of that shadow and how long it took to move, astronomers could estimate how far away the Moon must be. These estimates weren't perfect, but they began to suggest that the Moon was not just a nearby light in the sky. It was a world at a measurable distance. Aristarchus of Samos, the same Greek thinker who suggested the Sun was at the centre of the cosmos, also tried to measure the Moon's distance. He observed the angle between the Sun and the Moon during its quarter phase, when half the Moon appears illuminated. Using geometry, he attempted to calculate the relative distances of the Sun and the Moon. His results weren't precise, the methods were too limited, but the effort itself was remarkable. He was among the first to think of the Moon not just as a glowing object in the sky, but as something placed at a specific distance that could, in principle, be measured. Later, more refined methods emerged. By the Middle Ages, astronomers like al-Biruni in Persia and others across the Islamic world improved geometric approaches, using detailed observations of lunar eclipses and angular measurements. They came closer to the true distance, though still with significant error. What matters more than the numbers, though, is the principle. The Moon was no longer an untouchable mystery. It was something that could be studied scientifically. The real breakthroughs came with the development of telescopes. Suddenly, the Moon was revealed in astonishing detail. Craters, mountains, plains, all visible for the first time. It was no longer a smooth light in the sky, but a landscape, a place. With this came better measurements. Astronomers used parallax, the apparent shift in position of the moon against the background stars when viewed from different locations on Earth. By carefully measuring this shift and knowing the distance between their observation points, they could calculate the distance to the moon with surprising accuracy. Think about how ingenious that is. The moon is so far away that the shift is tiny, barely noticeable without careful instruments. Yet with patience and skill, astronomers could detect it, and from that sliver of difference, stretch their calculations across hundreds of thousands of kilometers. It was like holding up a finger at arm's length and shifting your head to see how it moved against the background, except the finger was the moon, and the background was the stars. By the 17th century, these methods had given estimates within a few % of the true value. That was an extraordinary achievement for the time. The moon's distance was no longer just a curiosity. It was a number, a measurable span of space. The universe had grown larger in human understanding, but also more tangible. If the moon's distance could be measured, then perhaps the distances to the planets, and eventually the stars, could be measured too. And then, of course, came the modern era, when the moon became not just something we measured from afar, but something we actually reached. In the 20th century, radar beams were bounced off the lunar surface, providing extremely precise measurements of its distance in real time. Later, during the Apollo missions, astronauts placed retroreflectors, special mirrors, on the lunar surface. Scientists on Earth could fire lasers at these reflectors and measure the time it took for the light to return. This gave distances accurate to within a few centimeters. The moon's distance, once guessed at with shadows and geometry, could now be tracked with exquisite precision. What makes this so powerful is not just the accuracy, but the continuity. The same question asked by early sky watchers, how far is it, was answered with increasing clarity across thousands of years. Each new method added detail, and each generation of astronomers stood on the work of those before them. From shadows to telescopes, from parallax to lasers, the story is one of human persistence in the face of immensity. But let's pause here and consider what the number itself means. 384,000 kilometers. It is such a large number that it's hard to grasp. If you could line up Earths between here and the moon, you could fit about 30 of them in the gap. That means if you shrank the Earth to the size of a basketball, the moon would be a tennis ball about 7 meters away. That doesn't sound far in that model, but in real terms the gap is vast. The emptiness between worlds is far larger than the worlds themselves. This perspective also changes how we think about the moon as part of our environment. It's not just a light in the sky, not just a marker of time. It's a separate world, orbiting at a great distance, bound to us by gravity. Its presence shapes tides, stabilizes Earth's tilt, and influences life in subtle but profound ways. Its distance is not just a number, it's part of why Earth is habitable at all. A closer moon would pull tides to extremes. A farther moon might not stabilize Earth's wobble, leading to wild climate swings. The actual distance, as it happens, is part of what makes Earth a stable home. There is also the emotional side of this measurement. When people first walked on the moon, they looked back at Earth and saw it hanging in the sky above the lunar horizon. From that vantage point, the Earth itself looked small and fragile. The distance between the two worlds, so immense when measured in kilometers, could be crossed in a few days of spaceflight. That paradox, vast yet crossable, unreachable for millennia yet suddenly visited, reshaped how people thought about the moon. It was no longer an unreachable lantern, but a destination. Even so, the distance remains humbling. Every time we look up and see the moon's bright disk, we're looking across nearly 400,000 kilometers of space. That span contains no air, no ground, no stepping stones, just a silent void. The moon hangs there, visible and familiar, but the space between is a reminder of scale. It tells us that even our closest neighbor in space is unimaginably far compared to human experience, and yet, in the grand scheme, it's just the first step. Once you've measured the moon's distance, you realise that the planets are farther still and the stars farther beyond that. The moon gives us a unit, a way to begin. It is the first rung on the ladder, the first measure of space beyond Earth itself. By climbing that rung, humanity began the long climb toward understanding the true immensity of the cosmos. So when you look at the moon tonight, think of that number, 384,000 kilometers. Think of the shadows measured in ancient wells, the careful records of eclipses, the parallax calculations, the radar pulses, the laser beams. Think of the astronauts who travelled that span, turning a number into a journey. After measuring the distance to the moon, the natural progression is to look farther still, toward the sun. It is, after all, the dominant presence in our sky, the reason we have daylight, the source of nearly all the energy that fuels life on Earth. For most of human history, it was taken for granted as simply what it appeared to be, a bright circle that rose and set. But as people began to study it more carefully, they discovered something astonishing. The sun is not just a nearby light. It is a colossal star, vastly larger than Earth, at a distance so great that even light takes minutes to cross the gap. Understanding its size and scale was one of the great achievements in humanity's journey to comprehend the universe. From Earth's surface, the sun doesn't look overwhelming. It is bright, of course. Too bright to look at directly without hurting your eyes, but its disk is small enough to be covered with a fingertip held at arm's length. That illusion of smallness is simply a trick of distance. In reality, the sun is enormous, so large that over 1 million Earths could fit inside it. Its diameter is about 1.39 million kilometers, more than 100 times that of Earth. Its mass is about 330,000 times greater. When you think of Earth as already vast, stretching more than 12,000 kilometers across, and then realize that the sun could swallow it many times over without noticing, the scale becomes difficult to hold in your mind. The question of how far away the sun is was one of the great puzzles of ancient astronomy. Early estimates varied widely. Some thought it might be only a few thousand kilometers away, close enough to be imagined as a kind of fiery object circling just above the Earth. Others, like Aristarchus, suspected it was far more distant, though they could not pin down the exact number. It wasn't until much later, with improved observations and instruments, that astronomers determined the average distance is about 149.6 million kilometers. That figure is now known as 1 astronomical unit, the baseline measure for distances within our solar system. Think about that number for a moment. 150 million kilometers. That's nearly 400 times farther than the moon. It means light, which moves at nearly 300,000 kilometers per second, takes just over 8 minutes to travel from the sun to Earth. Every ray of sunshine you feel on your skin in the morning is 8 minutes old, born in the core of the sun long before that, but only arriving after crossing that immense gulf of space. This distance alone makes the sun's apparent size in our sky remarkable. The fact that it appears about the same size as the moon, despite being vastly larger, is because it is also vastly farther away. That coincidence is what allows us to see total solar eclipses when the moon just happens to cover the sun's disk perfectly. As knowledge improved, people began to understand not only the distance but the true scale of the sun itself. Observations of its apparent size combined with the distance revealed its diameter. Calculations of planetary motions showed that its gravity must be immense, holding Earth and the other planets in orbit. The realization dawned that the sun contains nearly all the mass of the solar system, more than 99% of it. The planets, moons, and asteroids are leftovers, small in comparison, while the sun itself is the central engine. But size in kilometers and mass in numbers only go so far. To really understand the scale, comparisons help. Imagine shrinking the sun down to the size of a large beach ball. On that scale, Earth would be a tiny pea orbiting about 26 meters away. Jupiter, the largest planet in the solar system, would be about the size of a grapefruit, orbiting over 130 meters from the ball. That model makes it clear just how dominant the Sun is. The solar system is not really made of planets orbiting casually around a star. It is a system dominated by the Sun, with the planets as small companions circling at great distances. The immensity of the Sun also lies in its power. Every second it converts about 600 million tons of hydrogen into helium through nuclear fusion. This process releases energy equal to nearly 400 trillion watts. That number is almost impossible to comprehend, but put simply, the Sun produces more energy in 1 second than all of humanity has used in the entire course of history. That energy streams outward in all directions, lighting and warming Earth as only the tiniest fraction of the whole output. Yet that fraction is enough to sustain every plant, every ecosystem, every climate system on the planet. The size of the Sun, both in mass and in energy, is directly tied to our existence. Ancient cultures worshipped the Sun for this reason. Long before they knew the numbers, they understood that it was life-giving, that without its warmth nothing would grow. But the realization that it was not just a nearby godlike object, but a star, a ball of plasma larger than imagination, only deepened the sense of awe. For the first time, people began to see that the Sun was not unique in kind, only in proximity. The night sky was filled with other suns, so distant that they appeared as points. Our star was simply the one close enough to dominate our lives. That recognition changed everything about how people thought of the universe. It also raised new questions. If the Sun is a star, and stars are scattered everywhere, then how many are there? How far do they stretch? And if the Sun is this large, what does that say about the true scale of the cosmos? The Sun became the bridge between the familiar and the vast, between the warmth of daylight and the unimaginable immensity of the stars beyond. Astronomers have studied the Sun in detail, measuring its rotation, its layers, its spots, its flares. They've learned that the surface temperature is about 5,500 degrees Celsius, while the core reaches over 15 million degrees. They've watched waves ripple across its surface, storms erupt and calm, and streams of particles flow outward as solar wind. All of these details add to the sense of scale. This isn't just a sphere of light. It's a dynamic, powerful, enormous star with complex processes, each tied to its size and mass. From Earth, it feels permanent, unchanging. But in reality, the Sun is just one stage in a star's life. It has been shining for about 4.6 billion years and will continue for about another 5 billion before exhausting its hydrogen fuel. At that point, it will swell into a red giant, engulfing the inner planets, perhaps even Earth, before shedding its outer layers and leaving behind a white dwarf. The thought that something so vast, so dominant in our sky, is not eternal but subject to the same cycles as other stars adds another layer to our sense of perspective. Even the Sun, with its immense size, is just one star among countless billions, each with its own scale and lifespan. When you step outside and feel the warmth of sunlight, you're feeling the presence of something enormous beyond comprehension. The distance is immense, the size staggering, the energy output unimaginable, yet it feels personal. It warms your skin, lights your day, powers the plants that feed you. That duality, immense yet intimate, is part of what makes the Sun scale so compelling. It is the largest object in our sky, the central anchor of our solar system, and yet it connects directly to every moment of daily life. Measuring the Sun's size was not easy. It required centuries of progress, from geometry to telescopes to the physics of gravity. But each step reinforced the same truth. The universe is larger than we thought. If the Sun is this big and yet just one star among many, then the cosmos must stretch farther than anyone could imagine. The numbers are large, but the meaning is simple. We live in the light of a giant, and that giant is only the beginning of the vastness beyond. And so, the Sun serves as our introduction to scale on a stellar level. From Earth To the moon, and now to the sun, we've expanded our perspective from thousands of kilometers to millions. Soon we'll reach billions as we move to the stars and galaxies. Each step outward multiplies the immensity, but each step also begins with something close, something familiar, that reveals itself to be far more enormous than we first assumed. The sun is the clearest example of that. A disk that can be covered with your fingertip, yet so vast that it dwarfs our world. A nearby light that is, in truth, a star of colossal size linking us to the greater universe of stars beyond. Once the immensity of the sun becomes clear, the natural next step is to look at what shares space with us around it. The solar system is not just Earth and its companion moon circling a star. It is a neighbourhood filled with planets of astonishing variety, some so large that they could swallow Earth whole many times over, others so small that they are little more than icy pebbles drifting far from the light. To understand the scale of the universe, it helps to pause here, in our own neighbourhood, and consider how these worlds compare to one another. For much of history, only a few of these planets were known. The ones visible to the naked eye, Mercury, Venus, Mars, Jupiter and Saturn, were recognised by ancient skywatchers as different from the fixed stars. They wandered against the background, moving slowly but steadily, sometimes reversing their course in what we now know as retrograde motion. These wanderers became central to myths, calendars and early astronomy. Even without telescopes, their presence was undeniable. But their true scale, their true differences, were hidden until much later. When telescopes arrived in the early 17th century, the solar system began to expand. Galileo saw the moons of Jupiter, proving that not everything revolved around Earth. He noticed phases of Venus, showing it orbited the Sun. Later discoveries added Uranus, Neptune, and eventually the dwarf planet Pluto, though its status would later change. With each new world added, the neighbourhood grew, and so did the challenge of understanding how they all fit together in scale. Start with Mercury, the smallest planet and the one closest to the Sun. Its diameter is about 4,180 kilometres, less than half that of Earth. It has no atmosphere to speak of, just a rocky surface baked by the sun on one side and frozen on the other. Compared to Earth, it's tiny, yet it is still a world large enough to hold mountains, valleys, and craters stretching for hundreds of kilometres. Venus, by contrast, is nearly Earth's twin in size, with a diameter of about 1,200 kilometres. But its surface is radically different, hidden beneath thick clouds of carbon dioxide and sulfuric acid, with surface temperatures hot enough to melt lead. Two planets of similar size but radically different worlds. Then there's Mars, smaller than Earth with a diameter of about 6,800 kilometres, but still large enough to have its own volcanoes, canyons and polar caps. Olympus Mons, its great shield volcano, is the largest known in the solar system, towering more than twice as high as Mount Everest and stretching wider than the state of Arizona. Even on a smaller world, the scale can be immense. Mars reminds us that size doesn't always translate directly into significance. Beyond Mars lies the asteroid belt, a wide zone filled with countless rocky fragments. Most are small, but some, like the dwarf planet Ceres, are hundreds of kilometres across. These are like pebbles scattered between the larger worlds, remnants of material that never coalesced into a planet. Their presence shows that our neighbourhood has many scales at once, from tiny rocks to immense giants. And then come the true giants. Jupiter, the largest planet, has a diameter of about 142,000 kilometres, more than 11 times that of Earth. Its mass is more than 300 times greater. If Earth feels large to us, Jupiter dwarfs it utterly. It is a gas giant made mostly of hydrogen and helium with no solid surface. Its storms are vast enough to swallow Earth whole, like the famous Great Red Spot, a hurricane-like storm larger than our planet that has raged for centuries. Surrounding Jupiter are dozens of moons, some of them worlds in their own right. Ganymede, the largest moon, is bigger than Mercury. Europa, with its icy surface, hides an ocean beneath, a reminder that even small companions can hold vast secrets. Saturn, not much smaller than Jupiter, is equally awe-inspiring. With a diameter of about 120,000 kilometers, it too could contain Earth many times over. Its rings, made of countless icy particles ranging from tiny grains to mountain-sized chunks, stretch for hundreds of thousands of kilometers. The rings themselves are thin, only tens of meters thick in many places, but spread out in a dazzling display that makes Saturn unique in the solar system. Its moons are equally fascinating. Titan, larger than Mercury, has a thick atmosphere and lakes of methane and ethane on its surface. Enceladus, smaller but striking, has geysers that spray water vapor into space, hinting at a subsurface ocean. Even within Saturn's system, the scales vary dramatically, from immense gas giant to icy moons that might harbour life. Farther out, Uranus and Neptune complete the set of giant planets. Uranus, with a diameter of about 50,000 kilometers, is tilted so far on its axis that it essentially rolls around the Sun on its side. Neptune, slightly smaller but more massive, hosts fierce winds and storms, including the Great Dark Spot observed by Voyager 2. Both are ice giants, containing more ices and heavier elements than Jupiter and Saturn, and both remind us that even at the edges of the solar system, the scale remains immense. What becomes clear when looking at this neighbourhood is the staggering range of sizes, from Mercury, barely larger than our moon, to Jupiter, large enough to contain more than 1/300 Earths. The planets cover an extraordinary spectrum. Earth sits somewhere in the middle, larger than most, smaller than the giants, yet uniquely suited to life. It is easy to think of our world as the centre of things, but in the context of the solar system, it is simply one among many, neither the smallest nor the largest, but part of a continuum. And then there are the smaller bodies, dwarf planets, asteroids, comets, that remind us that scale doesn't end with the main planets. Pluto, once considered the 9th planet, is only about 377 kilometers in diameter, smaller than many moons. Eris, Haumea, Makemake, and other distant objects in the Kuiper belt expand the family further. Even beyond them, the scattered disk and Oort cloud may contain trillions of icy bodies, tiny compared to planets, yet vast in their numbers. These are the pebbles of the solar system, orbiting alongside the giants. When you step back and see the solar system as a whole, it becomes a neighbourhood of contrasts. Small rocky worlds near the sun, gas and ice giants farther out, and countless smaller fragments in between and beyond. The scale ranges from less than 3,000 kilometers across for tiny moons, to more than 140,000 kilometers for Jupiter, and all of it orbits one star, our Sun, which itself is just one among billions in the galaxy. The beauty of this perspective is that it shows how scale is relative. To us, Earth feels large and complete, but in comparison with Jupiter, it feels small. To Mercury, Earth would feel immense. To Jupiter, both would seem tiny. And to the Sun, even Jupiter is a small companion. The neighbourhood reminds us that there is no single measure of size that makes sense everywhere. It always depends on the frame of comparison. The planets also show us how diversity emerges in scale. Small worlds can have enormous features like Olympus Mons on Mars. Giant planets can have delicate structures, like Saturn's rings. Moons can rival planets in size, and dwarf planets can surprise us with complexity. Size is only one dimension of what makes a world interesting, but it's a powerful one, shaping atmospheres, surfaces, and the potential for life. As we continue outward, the neighbourhood of planets becomes the stepping stone toward the galaxy beyond. By learning the scale of these nearby worlds, we train our minds to accept larger scales still. We see that Earth is not alone, not unique in being a world, and not central in size. We learn that worlds come in many forms, from giants to pebbles, and that our solar system is just one example of what may exist elsewhere. And so the neighbourhood is both humbling and inspiring. It humbles us by showing that Earth is one among many, not the largest, not the smallest, but part of a spectrum. It inspires us by reminding us that if our solar system holds such variety, then the universe beyond may hold even more. The giants and the pebbles alike tell us that scale is layered, and that our place is one point in a much larger pattern. The solar system, in its range of sizes, becomes the bridge between Earth and the galaxy. It is the place where we learn to think in thousands of kilometres, then tens of thousands, then hundreds of thousands. It is where we see that even small bodies can matter, and that even giants exist within something greater. Once you've considered the variety of planets that orbit our Sun, the next natural thought is distance. It's one thing to compare their sizes, to imagine Earth next to Jupiter or Mercury, but another to ask how far apart they really are. The solar system is a neighbourhood of worlds, but it's a neighbourhood where the houses are not close together. They are separated by spaces so vast that even the speed of light begins to feel slow. The question becomes simple in words but complex in scale. How far is far when you're talking about the solar system? The first point of comparison is the distance between Earth and the Moon, because that was the first real step outward, almost 400,000 kilometres. That number alone is larger than most of us can picture, yet compared to what lies beyond, it is nothing. The Sun, our star, is nearly 400 times farther than the Moon. 150 million kilometres separate us from it, and yet we depend on that connection every moment. If you set out to cross that distance at the speed of a commercial jet, it would take you about 20 years of non-stop flight. At highway speeds, it would take more than 1,700 years. Distances in the solar system quickly overwhelm the imagination. When you look at the scale of orbits, the gap between each planet stretches the mind even further. Mercury orbits the Sun at an average distance of about 58 million kilometres. Venus is about 108 million. Earth, as we know, is at 150 million. Mars follows at 228 million. That means the gap between Earth and Mars is almost 80 million kilometres at its closest, and more than 400 million when the two planets are on opposite sides of the Sun. Crossing from one world to another isn't a matter of simply stepping across a gap. It means travelling across tens or hundreds of millions of kilometres, all while those worlds are moving in their orbits. Farther out, the scale expands in ways that hardly feel real. Jupiter orbits at 778 million kilometres from the Sun. Saturn is nearly 1.4 billion kilometres out. Uranus, 2.9 billion. Neptune, the most distant of the classical planets, circles at about 4.5 billion kilometres. These numbers are so large that they start to lose meaning in daily terms. To make them manageable, astronomers use the astronomical unit, the distance between Earth and the Sun, as a kind of yardstick. Jupiter is more than 5 astronomical units from the Sun, Saturn more than 9, Uranus about 19, Neptune about 30. Each unit is 150 million kilometres, but by reducing the numbers to smaller figures, the scale becomes easier to grasp, even if the immensity remains. To travel across these distances with spacecraft has been one of humanity's most ambitious undertakings. The Voyager probes, launched in the late 1970s, gave us our first direct tours of the outer planets. Voyager 1, still travelling today, is the most distant human-made object in existence, having crossed into interstellar space. At its fastest, it covered nearly 1 million kilometres per day, and yet it took years to pass each planet, and decades to move beyond the outer edge of the solar system. Even moving at such extraordinary speeds, crossing the system is a long and patient journey. Another way to think about distance is through light itself. Light from the Sun takes 8 minutes to reach Earth. It takes about 43 minutes to reach Jupiter, over an hour to reach Saturn, 2.5 hours to reach Uranus, and more than 4 hours to reach Neptune. Signals sent from Earth to spacecraft at those distances take just as long to return. When Voyager communicates from the edge of the solar system, Its messages are over 20 hours old by the time they arrive. Even at the fastest speed known, the speed of light, the solar system is not small. Consider what this means for scale. Earth feels vast because circumnavigating it is a journey of 40,000 kilometers. The Moon feels far at nearly 400,000 kilometers. The Sun is distant at 150 million. But Neptune is 30 times farther still at 4.5 billion. The numbers increase by orders of magnitude, each step outward making the previous one feel small. To cross the solar system is to move from thousands of kilometers to millions to billions, a progression that quickly leaves human experience behind. The space between planets also contains more than emptiness. The solar wind flows outward from the Sun, carrying charged particles across billions of kilometers. Magnetic fields stretch and interact. Dust and comets drift silently. Asteroids orbit in belts and clouds, some near, some far. All of this is part of the solar system's scale. The distances are immense, but they are not barren. They are filled with subtle, invisible processes that connect the whole system together. When we imagine crossing the solar system, we often picture a spaceship moving steadily from one planet to the next. In reality, travel is dictated by orbits, speeds, and energy. To reach Mars, spacecraft must launch at just the right moment, when Earth and Mars are aligned favourably to minimise the distance. Even then, the journey takes months. To reach Jupiter or Saturn takes years. Voyager's path used gravity assists, swinging around planets to gain speed, carefully planned to make the most of rare alignments. Crossing the solar system is not a straight line. It is a dance with gravity, each move calculated, each distance immense. For perspective, imagine shrinking the solar system into a model. If the Sun were the size of a large orange, Earth would be a tiny pinhead about 10 meters away. Jupiter, a marble, would be 50 meters out. Neptune, a grain of sand, would sit 300 meters from the orange. The entire system would stretch across a city block, yet the planets themselves would be nearly invisible compared to the gaps between them. That is the reality of scale. Vast spaces punctuated by relatively tiny worlds, and even that model leaves out the outer regions. Beyond Neptune lies the Kuiper Belt, a vast zone of icy bodies, including Pluto and Eris, stretching billions of kilometers further. Beyond that still is the hypothesized Oort cloud, a shell of comets that may extend up to 100,000 astronomical units from the Sun. That distance is so great that light would take more than a year to travel across it. If the solar system truly includes the Oort cloud, then its size is beyond comprehension, a bubble of influence stretching deep into interstellar space. When you think about how far is far, it helps to remember that most of these distances were unknown to early astronomers. They could see the planets, they could track their motions, but the true scale was hidden. Only with careful observation, mathematics, and eventually spacecraft did the numbers reveal themselves, and when they did, they showed a system far larger than anyone had guessed. The solar system is not a tight cluster of worlds circling a sun. It is a sprawling expanse with distances so great that they redefine our sense of space. There is something humbling about realizing that even within our own system, the distances are nearly insurmountable by human standards. We have visited the Moon, sent robots to Mars, and flown probes past the outer planets, but the gaps remain immense. Crossing the solar system is an achievement not measured in days or months, but in decades and generations. It shows us that space is not a backdrop but a vast environment, where distance itself is one of the greatest challenges. And yet, for all its immensity, the solar system is still small compared to the galaxy. Crossing from one end of our neighbourhood to the other takes billions of kilometres, but the nearest stars lie trillions of kilometres beyond. The solar system is vast in human terms, but it is only the first step outward in cosmic terms. Asking how far is far in the solar system prepares us to ask how far is far among the stars and then among the galaxies. For now, though, it is enough to recognise the scale of our home system. From Earth to the Moon, From Earth to the Sun, from Earth to Neptune, the distances multiply, each step greater than the last. The planets are neighbours only in the sense that they share the same star. In reality, they are separated by gulfs of space so wide that they defy everyday experience. To cross them is to move through billions of kilometres of emptiness, guided by gravity and light. That is the true scale of the solar system. Far is not just far. Far is almost beyond imagining. As far as the solar system stretches, with planets orbiting billions of kilometres from the Sun, there is still an outer boundary where the influence of our star begins to fade. This is not the edge of the universe, or even the edge of the galaxy, but it is the edge of the Sun's reach, the point where its constant breath of particles and magnetic fields finally meets the wider environment of interstellar space. This region is called the heliosphere, and it is far larger and more complex than early astronomers could have imagined. To understand the true size of the solar system, it is not enough to measure orbits. We also have to measure influence. The Sun is not silent. It emits more than light and heat. It also streams a constant flow of charged particles, mostly protons and electrons, that spread outward in all directions. This is the solar wind, a river of plasma that fills the solar system and beyond. The solar wind carries the Sun's magnetic field with it, shaping space itself. It creates auroras on Earth, interacts with planetary atmospheres, and sculpts long tails on comets as they pass. But most of all, it defines the bubble in which our solar system sits. That bubble, the heliosphere, is vast. Imagine Earth orbiting at 150 million kilometres from the Sun. Now imagine Neptune at 4.5 billion kilometres. The heliosphere extends at least 20 times farther than that. Estimates place its boundary, called the heliopause, at around 120 astronomical units, or more than 18 billion kilometres from the Sun. At that distance, light takes over 16 hours to travel. Spacecraft launched in the 1970s are only now beginning to cross it. Compared to the Oort cloud, the heliosphere may be small, but compared to human experience, it is immense beyond reckoning. The heliosphere is not a perfect sphere. It is shaped by the interaction between the solar wind and the interstellar medium, the thin gas and particles that fill the space between stars. As the solar wind pushes outward, the interstellar medium pushes back, creating a boundary layer. Inside this bubble, the Sun's particles dominate. Outside, the particles of the galaxy flow freely. It is a frontier, not marked by any visible wall, but by changes in particle density, magnetic field direction, and cosmic ray intensity. The first direct evidence of this boundary came from spacecraft. Voyager 1, launched in 1977, travelled past Jupiter and Saturn, then continued outward. By 2012, it crossed the heliopause, becoming the first human-made object to leave the heliosphere and enter interstellar space. Its instruments detected a sudden increase in cosmic rays and a shift in magnetic fields, confirming that it had passed the boundary. Voyager 2 followed, crossing in 2018. These spacecraft, carrying golden records of Earth sounds and images, became our ambassadors to the stars, proving that the Sun's reach has a limit. What makes this concept fascinating is that it redefines what we mean by the solar system. If you measure only by planets, then Neptune or Pluto might mark the edge. But if you measure by the Sun's influence, then the heliosphere stretches far beyond. The solar system is not just a set of orbits. It is a bubble of space shaped by the energy of our star, and that bubble is enormous. Inside the heliosphere, cosmic rays from distant stars and galaxies are partially shielded. The solar wind deflects many of them, reducing their intensity. This shielding is not perfect, but it creates a protective environment for planets like Earth. Without it, life would be exposed to far more high-energy radiation. The heliosphere is not just a boundary of influence, it is a kind of shield, a barrier that makes our planetary neighbourhood more hospitable. The scale of the heliosphere also helps us appreciate the immensity of interstellar space. Beyond the heliopause, There are no more planets of our solar system, no more orbits to measure. Instead, there is only the thin gas of the galaxy, spread across trillions of kilometers. The fact that our star carves out a bubble in that vastness is a reminder of how stars shape their surroundings. Every star has its own bubble, its own sphere of influence. Our heliosphere is just one among billions in the galaxy, each overlapping, each touching, each defining a region of space. To picture it, imagine shrinking the solar system again. If the distance from Earth to the Sun were the length of a single step, then Neptune would be 30 steps away. The heliopause would be more than 100 steps beyond that, out where the neighbourhood becomes a vast field. It shows just how much farther the Sun's reach extends compared to the orbits of its planets. The planets are only the beginning. The heliosphere is the true measure of the Sun's domain, and yet, even at its enormous scale, the heliosphere is tiny compared to the distances between stars. The nearest star system, Alpha Centauri, lies about 270,000 astronomical units away. That's more than 2,000 times farther than the edge of the heliosphere. In other words, if the heliosphere were a bubble the size of a beach ball, the nearest star's bubble would be another beach ball placed more than 2 kilometers away. Between them would be emptiness, a void so vast that even the immensity of the heliosphere seems small. The edge of the Sun's reach, then, is not an end but a threshold. Crossing it doesn't mean leaving the universe. It means stepping from one domain of influence into another, from the familiar shelter of the Sun's wind into the open sea of the galaxy. For spacecraft like Voyager, it was a milestone, a point where the numbers shifted, the environment changed, and the data proved that human-made objects had entered a new region. For us, it is a reminder that even the greatest reach of our star is finite, that beyond it lies something larger still. It also raises questions about the nature of boundaries in space. The heliosphere is not a wall but a gradual transition, where solar particles thin out and interstellar particles increase. It moves with the Sun, shaped by the relative motion of our system through the galaxy. It expands and contracts with the solar cycle, breathing in and out with the rhythms of our star. It is dynamic, not fixed, a frontier that shifts with time. To measure it is to study not just distance, but interaction, the meeting of forces on a cosmic scale. For humanity, the heliosphere has practical importance as well. Understanding it helps us protect spacecraft, predict cosmic radiation, and learn how stars shape their environments. It tells us about the journey of particles, the structure of magnetic fields, and the processes that influence planets. In this sense, the edge of the Sun's reach is not just an abstract concept. It is part of the conditions that make life on Earth possible, part of the system that defines our place in space. When you think about how large the universe is, it is easy to skip past the heliosphere. It feels local, limited to our solar system. But in reality, it is one of the first true hints of cosmic scale. It shows us that stars do not simply sit alone in the void. They shape vast regions around them. They influence space across billions of kilometers. They define domains within the galaxy. The heliosphere is our star's domain, and by measuring it, we begin to see ourselves as part of something larger than just planets orbiting a sun. And so, the edge of the Sun's reach becomes a stepping stone. From Earth to the Moon, to the Sun, to the planets, and now to the heliosphere, we have moved steadily outward, multiplying our sense of distance at each stage. The heliosphere reminds us that even when planets end, the Sun's influence continues, stretching farther than orbits, farther than sight, into a bubble that touches the stars. It is not the end of space, but it is the edge of home, the place where the familiar presence of our star fades and the immensity of the galaxy begins. Once you've crossed the boundary of the Sun's reach, the question that naturally follows is what lies beyond. The answer, in the simplest sense, is stars. They are the points of light we've seen all our lives, scattered across the night sky in patterns that seem familiar, yet each of them is its own world, its own sun, with its own domain stretching outward. To understand the true size of the universe, we have to begin by measuring the distance to these nearest neighbours. The numbers are larger than anything we've encountered so far, and they begin to show us why the galaxy is a place of almost unimaginable scale. The closest star system to us is Alpha Centauri, a group of 3 stars. 2 of them, Alpha Centauri A and B, are sun-like stars orbiting one another, while the third, Proxima Centauri, is a smaller red dwarf circling farther out. Proxima happens to be the closest of all, lying about 4.24 light-years away. To say light-years is to use a measure that already contains distance and time. 1 light-year is the distance light travels in a year, about 9.5 trillion kilometres. So Proxima Centauri, though the nearest star, is still more than 40 trillion kilometres from Earth. Numbers that large are almost impossible to visualise. Even with spacecraft like Voyager travelling at tens of thousands of kilometres per hour, it would take over 70,000 years to reach the nearest star. The gap between stars is not like the gap between planets. It is thousands of times greater, a void so immense that for most of history it seemed unreachable, and yet we've managed to measure it. That achievement, perhaps more than anything else, shows the power of human curiosity and ingenuity. The method that first made it possible is parallax. It's a simple concept, something you can see with your own eyes. Hold out your finger at arm's length and close one eye, then switch to the other. Your finger seems to shift against the background. That shift is parallax, caused by viewing from 2 different positions. Astronomers realised that Earth itself provides 2 vantage points as it moves around the Sun. By observing a nearby star in January, then again in July, they could measure its tiny shift against the background of more distant stars. The angle of this shift, though incredibly small, could be used to calculate the star's distance. The challenge is that even the nearest stars show only the faintest parallax. The shifts are fractions of an arc-second, smaller than the apparent size of a grain of sand seen from kilometres away. For centuries, astronomers tried and failed to detect it. Telescopes weren't precise enough, measurements weren't steady enough, and the stars seemed stubbornly fixed. But in the 19th century, persistence paid off. Friedrich Bessel in 1838 successfully measured the parallax of a star called 61 Cygni. His result placed it about 10 light-years away. For the first time, humanity had measured the true distance to a star. The universe had suddenly expanded by orders of magnitude. After that breakthrough, more stars were measured, each one revealing distances of light-years, not millions or billions of kilometres, but trillions upon trillions. The nearby stars form a kind of neighbourhood, but even in that neighbourhood the spaces are vast. Barnard's star, about 6 light-years away, is among the closest. Sirius, the brightest star in the night sky, lies just over 8 light-years away. Vega, famous from countless myths and stories, is about 25 light-years distant. Even stars that look side by side in constellations are usually separated by tens or hundreds of light-years. The sky is not a dome but a 3-dimensional scattering, each star a beacon at a different distance. Parallax gave us the first rung of the cosmic distance ladder. With it, astronomers could measure hundreds and eventually thousands of stars. Modern space telescopes like Hipparcos and Gaia have extended this to millions, providing maps of our galaxy in extraordinary detail. But even before those tools, once a few distances were known, they could be used to calibrate other methods, like the brightness of certain types of stars, allowing astronomers to measure far beyond parallax's reach. Each step outward required careful building on the last, and it all began with those first tiny shifts. The significance of measuring stellar distances cannot be overstated. Before parallax, stars were mysterious lights, their scale unknown. Afterward, they became suns, each at a distance that redefined our place. It proved that the universe was not a small system of spheres, but a vast expanse of space dotted with stars at enormous intervals. The nearest neighbour was trillions of kilometres away, and beyond it lay countless others. Consider what that means for perspective. The solar system, with its billions of kilometres, feels immense to us. Yet compared to the distance to even the nearest star, it is a tiny bubble. The heliosphere may extend 120 astronomical units, but Proxima Centauri lies more than 260,000 astronomical units away. That makes our entire solar system seem like a speck in the interstellar gulf. To measure that gulf is to begin to see just how small our neighbourhood is in the larger scheme. There is also a subtle beauty in realising that starlight itself carries distance. When you look at Proxima Centauri with a telescope, you're seeing light that left it over 4 years ago. When you see Sirius, you're seeing it as it was 8 years ago. When you gaze at Vega, you're looking back a quarter of a century in time. The distances are so great that looking outward is also looking backward. Each star is not just far away in space, but in time. This connection between distance and history makes the act of measuring even more profound. The stellar neighbourhood also reminds us of the diversity of stars. Some, like Proxima Centauri, are small and faint, barely visible without a telescope. Others, like Sirius, are bright and massive. Still others, like Betelgeuse in Orion, are supergiants, hundreds of times the size of the Sun, glowing red from their sheer immensity. The distances to these stars vary, but all of them together form the fabric of our galaxy. Measuring their distances shows us not just how far they are, but how many there are and how they are distributed. As our tools improved, so did our reach. Space telescopes have now measured parallaxes with extraordinary precision down to microarc seconds. This allows astronomers to chart distances not only to nearby stars but to clusters and regions far across the Milky Way. The map that emerges is breathtaking. Stars are not randomly scattered. They form patterns, spiral arms, clusters and associations. The distances reveal structure, and the structure reveals scale. And yet, for all this progress, the numbers remain humbling. The nearest star is over 4 light-years away. The width of the Milky Way is over 100,000 light-years. That means the nearest stars are like grains of sand at arm's length, while the galaxy is like an entire desert stretching beyond sight. Measuring the distances to stars is like dipping a cup into an ocean. Each measurement is precise, but together they only hint at the immensity beyond. What makes this step so important in our journey is that it marks the transition from solar scale to galactic scale. Within the solar system, distances are measured in astronomical units, millions or billions of kilometres. Beyond, among the stars, the light year becomes the only unit large enough to make sense. It shifts our thinking, expands our vocabulary, and forces us to accept numbers that stretch far beyond daily comprehension. The story of how humanity measured these distances is also a story of patience and persistence. For centuries, people suspected the stars were far away but could not prove it. They searched for parallax in vain, frustrated by the limitations of their instruments. When Bessel finally succeeded, it was not just a technical achievement, it was a philosophical one. It proved that the stars were truly suns at vast distances, and that the universe was far larger than any previous model had suggested. That realization still resonates today. So when you look at the night sky and see the stars twinkling above you, remember that each is not just a point of light, but a sun separated from us by trillions of kilometers. The nearest are already beyond easy reach, and most are unimaginably farther still. Yet we have managed to measure them, to put numbers to the gulfs of space, to begin mapping our place among them. These are our stellar neighbours, close in cosmic terms, yet distant in every sense we can imagine. Once the distances to the stars began to reveal themselves, astronomers quickly realised that ordinary measures no longer worked. Kilometres and miles, useful for roads and oceans, even for the size of planets, became meaningless when stretched across trillions. The human mind struggles with numbers that large because we have no frame of reference for them in daily life. Out of necessity, a new measure emerged, one that linked distance to something fundamental and universal: the speed of light. The light year became not just a unit, but a way of thinking, a bridge between space and time, and a reminder that in the universe the two are inseparably woven together. Light moves faster than anything else we know, about 300,000 kilometers per second in a vacuum. In 1 second, it can circle Earth more than 7 times. In 1 minute, it can travel 18 million kilometers. In 1 hour, more than 1 billion kilometers. Stretch that across a year, and the distance is about 9.5 trillion kilometers. That is 1 light year. The term sounds simple, but the number it represents is staggering. It's almost too large to compare with anything familiar. Even the entire orbit of Neptune around the Sun, the edge of the classical solar system, is less than 1,000th of a light year across. What makes the light year so powerful is that it ties distance directly to time. When we say that a star is 4 light years away, we mean not just that it is trillions of kilometers distant, but that its light has taken 4 years to reach us. When you look at that star tonight, you are seeing it as it was 4 years ago. The farther out you look, the older the image becomes. Light from Sirius left it over 8 years ago. Light from Vega began its journey 25 years ago. Light from Betelgeuse started more than 600 years ago, long before the telescope was invented. The night sky is not a view of the universe as it is now, but a patchwork of different times, all layered together. This connection between space and time is profound. It means that astronomy is also a kind of archaeology. To study the sky is to look into the past. Every telescope is a time machine, not because it transports us physically, but because it captures ancient light, carrying with it a record of how things once were. The farther away an object is, the older the story it tells. Galaxies billions of light years away show us the universe as it was billions of years ago, when it was young. In this way, distance and history become inseparable. The light year also helps us manage scale emotionally. It gives us a language that feels natural once you get used to it. Saying a star is 10 light years away feels easier to grasp than saying it is 95 trillion kilometers. Saying a galaxy is 100 million light years away makes the immensity sound almost comprehensible, even though the numbers behind it remain beyond direct experience. The unit is not just practical, it is psychological, giving us a way to talk about the incomprehensible. Think about the implications for daily starlight. When you look at the Pleiades, the cluster of stars sometimes called the Seven Sisters, you're seeing light that left them about 400 years ago. When you admire the Andromeda galaxy on a clear night, you're seeing light that began its journey more than 2.5 million years ago, before modern humans even existed. The photons striking your eye tonight began their trip when our ancestors were still using stone tools. Every star and galaxy is a message from the past, carried on beams of light that travelled across space and time to reach you in this moment. This also means that the farther out we look, the more we can learn about cosmic history. By measuring light from distant galaxies, astronomers can study how stars formed, how galaxies evolved, how the universe itself changed over billions of years. The light year is not just a measure of distance, it is a timeline, a ruler laid across the history of everything. Each number carries both space and time, both position and age. It also reshapes our sense of scale within the galaxy. The Milky Way is about 100,000 light-year across. That means light itself takes 100,000 years to travel from one edge to the other. If you could ride a beam of light, you would pass generations of human history before reaching the far side of our own galaxy. The distances between stars may be measured in a handful of light years, but across the galaxy the numbers climb into the tens of thousands. Between galaxies they reach into the millions, and between clusters of galaxies into the billions. The light year is the unit that keeps pace with this immensity. There's something grounding about linking distance to light. Light is part of daily experience. We see it every time we open our eyes. We feel it as warmth from the sun. We measure our days by it. to take that familiar phenomenon and use it as the ruler of the cosmos, connects the ordinary to the extraordinary. It means that the same thing that lets you see the pages of a book or the face of a friend is also what lets you glimpse the edges of the universe. The light year is not abstract. It is built from the most basic experience of being alive, and yet the numbers remain humbling. 1 light year is already vast beyond imagination, and the nearest star is more than 4 of them away. The farthest objects visible with the naked eye, like the Andromeda Galaxy, are millions of light years distant. The most remote galaxies detected by telescopes lie over 13 billion light years away. When we talk about the size of the universe, we're talking in units that already contain trillions of kilometers, multiplied billions of times. The light year may make the numbers easier to say, but it does not make them less immense. This way of thinking also forces us to accept that the universe we see is not the universe as it is now, but as it was. Because light takes time to travel, every observation is a look backward. The present state of distant galaxies is unknown to us. We see them frozen in time, long ago. Some of the stars we admire in the sky tonight may already have changed, or even died, their current state hidden from us until their newer light finally arrives. The light year is not just a distance, it is a veil, separating us from the present reality of the cosmos. Astronomers embrace this, turning it into a tool. By gathering light from different distances, they reconstruct a timeline of cosmic history. Closer stars show us the present galaxy. Distant galaxies show us the early universe. Together they create a record of billions of years written in light. Without the concept of the light year, none of this would be possible. It is the unit that translates between here and there, now and then, making sense of a universe that is too large to measure otherwise. For us, sitting under the night sky, the light year also changes how we feel about stargazing. It means that looking up is not just looking out, but also looking back. It means that the universe is not only vast in space, but layered in time. It means that our moment is connected to countless others, spread across billions of years, all arriving together as light in the sky. It is humbling, but also strangely comforting. The stars are distant, but their light has come all this way, carrying with it the history of the cosmos. And so, the light year is more than a number, it is a way of seeing. It reminds us that distance and time are woven together, that every observation is a glimpse into the past, that the universe is not just a place, but a story unfolding across ages. It is the unit that bridges our small lives with the larger scales imaginable, turning the ordinary speed of light into the ruler of everything. When we look at the night sky on a clear, dark evening, away from the glare of cities, one feature stands out above all others. A faint band of light stretches across the heavens, pale and hazy, as though someone had brushed a streak of cloud from one horizon to the other. For most of human history, that band was a mystery. It looked different from stars, more like a mist or a spill of milk, which is how it earned its name, the Milky Way. Today, we know what it really is. Not a cloud, not a trick of the atmosphere, but the combined light of billions of stars too distant and too faint to distinguish one from another. That soft band is the structure that holds us, our home galaxy, and it is vast beyond anything we've considered so far. The Milky Way is a barred spiral galaxy, a collection of hundreds of billions of stars arranged in sweeping arms that curl around a dense central bulge. Our solar system sits about 27,000 light-years from the centre, in one of those spiral arms called the Orion Arm. From our position, we see the galaxy edge on, which is why it appears as a band across the sky. When you look at that hazy streak, you are gazing into the thickness of the disk where stars are packed together more densely than in other directions. The stars you see in constellations are all relatively close, within a few hundred or a few thousand light-years. The Milky Way itself stretches more than 100,000 light-years across. That number is staggering. 100,000 light-years. It means that if you could somehow travel at the speed of a light, the fastest speed possible, it would still take 100,000 years to go from one edge of the galaxy to the other. For comparison, modern humans as a species have only existed for about 300,000 years, so the entire history of humanity is barely 3 galactic crossings at light speed. That gives a sense of just how immense the Milky Way is. To put it another way, the diameter of the galaxy is more than 1,000 times the distance to the nearest star. Crossing from one edge to the other would involve passing hundreds of billions of stars, countless planets, and vast clouds of gas and dust. Even our most advanced spacecraft, travelling at tens of thousands of kilometres per hour, would need longer than the age of the universe itself to complete the journey. Walking across it, as the title suggests, is so far beyond possible that it almost becomes absurd. Yet imagining the attempt gives perspective. Our world, our solar system, even our stellar neighbourhood, all fit comfortably within a tiny fraction of this great disk. The structure of the Milky Way is layered and complex. The disk is thin compared to its diameter, only about 1,000 light-years thick in most places. Above and below the disk lies the galactic halo, a sparse sphere of older stars and globular clusters, as well as dark matter that outweighs the visible galaxy. At the centre is a bulge tens of thousands of light-years across, crowded with stars and containing a supermassive black hole known as Sagittarius A. This black hole has a mass of about 4 million suns, anchoring the motions of stars in the central region. The spiral arms radiate outward, filled with young stars, nebulae, and regions of star formation, places where the galaxy continues to build itself. Our position, in one of the quieter arms, is fortunate. Being too close to the centre would mean living among crowded stars, frequent supernovae, and intense radiation. Being too far out might mean isolation, with fewer heavy elements needed for planets and life. Where we are in between is a kind of galactic suburb, far from the busiest neighbourhoods but close enough to have the resources we need. It gives us a clear vantage point, a stable environment in which to develop, and a chance to look outward. The sheer number of stars in the Milky Way is also astonishing. Estimates vary, but most place it between 100 and 400 billion. That means that for every person on Earth, there are tens of thousands of stars in our galaxy alone. Many of these stars have planets. In recent decades, astronomers have discovered thousands of exoplanets orbiting other suns, and statistical models suggest that there may be billions of Earth-sized planets in the Milky Way. The galaxy is not just immense in space, it is immense in possibility. Each star is a potential system, each system a potential home for life. Measuring the size of the Milky Way has been a long and difficult process. From Earth, embedded in the disk, we cannot step outside and look back. For centuries, people imagined the galaxy as much smaller, because they could only see as far as their instruments allowed. It wasn't until the 20th century, with better telescopes and the discovery of variable stars whose brightness could be used to gauge distance, that astronomers realised the true scale. The work of Edwin Hubble and others revealed that not only was the Milky Way vast, but it was not the entire universe. Other galaxies lay beyond, equally immense, filling space far outside our own. But even before those discoveries, understanding the scale of the Milky Way alone was enough to transform humanity's sense of place. Think about the timeline involved. Light takes 8 minutes to travel from the Sun to Earth. It takes just over 4 years to travel from Proxima Centauri, our nearest star. But to cross the Milky Way, it takes 100,000 years. That span is longer than recorded human history by far. It means that any signal we send to the other side of the galaxy will arrive to a future so distant that civilizations could rise and fall in the meantime. Communication across the Milky Way is not just difficult, it is practically a conversation across epochs. The galaxy also provides context for the life cycles of stars. Within its arms, stars are born from clouds of gas, live for millions or billions of years, and eventually die, scattering their material back into space. Supernovae seed the galaxy with heavy elements, building the ingredients for planets and life. Our own Sun is a second or third generation star, enriched by the remnants of older stars that came before it. The Milky Way is not static. It is alive with motion, with birth and death, with processes that span billions of years. Its immensity is not just in size, but in time. When you look up at the band of the Milky Way, what you are seeing is only a tiny fraction of its stars, those bright enough and near enough to combine into visible haze. Most of its stars are too faint, their light lost in the background glow. Telescopes reveal far more, showing clusters, nebulae, and dense star fields that stretch endlessly. The faintness of the band is misleading. It is not a sign of scarcity but of excess. There are too many stars to resolve. They blend together into light. The Milky Way also moves as a whole. Our solar system orbits the galactic centre at about 828,000 kilometers per hour, completing one orbit roughly every 225 million years. That means since Earth formed 4.5 billion years ago, it has circled the galaxy about 20 times. During that journey, the galaxy itself has also moved, drawn by the gravity of nearby galaxies, orbiting within a larger structure called the local group. The immensity of the Milky Way is only part of a larger immensity, but it is the part we belong to most directly. To imagine walking across the Milky Way, as the phrase suggests, is to highlight the absurdity of scale. If you could walk at a steady pace of 5 kilometers per hour without stopping, it would take about 20 million years to reach the other side. Even imagining travelling at the speed of light, the numbers remain overwhelming. Yet thinking this way helps us understand that our solar system is just a small detail, a tiny speck within a structure too vast for direct experience. It also helps us appreciate the quiet miracle of being able to glimpse it at all. That faint band in the night sky is a glimpse of something so large that words strain to hold it. When you stand under the night sky, what you see with your eyes is only a hint of what's really there. A few thousand stars at most, scattered in patterns that humans have traced into constellations for stories and navigation. It feels like a lot, enough to inspire myths and guide travellers across oceans, enough to make the sky feel full. But in reality, that handful of visible stars is a tiny fraction of the true number. The Milky Way holds hundreds of billions of stars, perhaps even more than that, and when you realise how many are hidden beyond the reach of your eyes, the scale of the galaxy begins to reveal itself in earnest. The idea of counting stars has fascinated people for as long as records exist. Ancient observers would lie on their backs and try to count the points of light, only to find themselves overwhelmed. Even in the clearest skies, far from city lights, the stars blur together, forming a haze that resists individual tallying. The Greeks estimated that a few thousand stars filled the sky. The Chinese kept detailed star catalogues with similar counts, but all of these were based on what the naked eye could see. It was only with telescopes that the true immensity began to emerge. When Galileo first pointed his telescope toward the Milky Way, he described what he saw with awe. The hazy band, which had looked like a smear of cloud to the naked eye, resolved into countless tiny stars, far too many to count individually. The mist was not a mist at all. It was the combined light of billions of suns, each too distant and faint to stand out on its own. That realization changed everything. The Milky Way was not an atmospheric effect, not a trick of perception, but a vast system of stars spread across space. Counting them was no longer a matter of tallying points. It became a question of measuring the galaxy itself. Astronomers began cataloguing what they could. Star by star, cluster by cluster, they built lists, maps, and surveys. In the 18th century, William Herschel attempted a systematic approach. He counted stars in different regions of the sky through his telescope, reasoning that the density of stars in each direction would reveal the shape of the galaxy. His results suggested a disk-like structure, with the sun somewhere near the centre. He was wrong about our position, but the method was sound. By counting stars, he had begun to map the Milky Way. Today, with modern instruments, the counts are far beyond what Herschel could have imagined. Surveys suggest that the Milky Way contains between 100 and 400 billion stars. The uncertainty comes not from lack of effort, but from the sheer scale and complexity of the galaxy. Dust clouds obscure much of the light, hiding stars from view. Some stars are faint red dwarfs, barely glowing, so dim that they outnumber brighter stars by far but remain difficult to detect. Others are hidden in the dense bulge near the centre, or in clusters far above and below the galactic disk. To count them all requires careful extrapolation from what we can see. Consider the diversity of those stars. Many are small red dwarfs, cooler and dimmer than the Sun, but incredibly common. They make up perhaps 3/4 of all stars, tiny but numerous, a population of trillions across the universe. Some are sun-like, burning steadily for billions of years, with the potential to host planets and life. A smaller number are massive blue giants, burning brightly but living briefly, destined to explode as supernovae. Still others are white dwarfs, the remnants of stars that have already ended their lives, faint embers glowing in the dark. Counting stars means counting all of these, from the faintest dwarfs to the brightest giants, each contributing to the galaxy's light in its own way. The challenge is not just the number, but the scale of variation. Stars range from less than 1/10, the mass of the Sun, to more than 100 times its mass. Their brightness varies by factors of millions. Their lifespans range from a few million years to trillions. To count them is not just to tally points, but to embrace an entire spectrum of cosmic diversity. Each star is a story of formation, life and death. Multiply that by billions, and you have the swirl of the Milky Way. For a sense of scale, imagine standing on Earth and looking at the sky. If every star in the galaxy were bright enough to be visible, the night would never be dark. The entire dome of the sky would be filled with light, brighter than the Sun, overwhelming our vision. The fact that it isn't is simply because most stars are too far, too faint, their light spread too thin. The night sky we see is not the full picture. It is a quiet whisper of a much louder chorus. Modern missions have transformed our ability to count stars. The Gaia spacecraft, launched by the European Space Agency, has measured the positions and motions of over 1 billion stars with exquisite precision. That number alone is staggering, yet it represents only about 1% of the galaxy's total. Even with 1 billion stars charted, the vast majority remain unmeasured. The galaxy is so full that even the most ambitious surveys can only sample a fraction. But from those samples we can estimate the whole, arriving at the billions upon billions that define the Milky Way. What does it mean to live in a galaxy of hundreds of billions of stars? On one level it is humbling. Earth, our solar system, our lives, are only one among uncountable others. The Sun is an ordinary star, not remarkable in mass or brightness, one dot among billions. On another level, it is inspiring. If stars are so numerous, then planets must be too. If planets are so common, then the potential for life may be equally vast. Counting stars is not just an exercise in astronomy. It is a way of framing the possibilities of existence. There is also the matter of perspective. The stars we see in the sky, the ones that form constellations, are all within a few thousand light years. That means they are the tiniest fraction of the galaxy, the nearest neighbours in an ocean that stretches 10 times farther in every direction. When we say the Milky Way contains hundreds of billions of stars, what we mean is that our familiar night sky is like a drop of water from a vast ocean. The patterns we know are local. The true scale lies beyond sight. Counting stars also reminds us that galaxies are not uniform. Stars cluster together in groups, associations and clusters. Some regions are dense, with stars packed close, while others are sparse. Globular clusters, for example, contain hundreds of thousands of stars in a sphere only a few dozen light-years across. Open clusters are looser. groups of young stars formed from the same cloud. In the galactic centre, stars are crowded together, orbiting rapidly around the central black hole. In the outer regions, they are more widely spaced, drifting in the quiet suburbs of the galaxy. To count stars is to embrace this structure, this complexity, this variety, and even beyond our galaxy, the numbers multiply. The Milky Way is only one galaxy among perhaps 2 trillion in the observable universe. If each contains hundreds of billions of stars, then the total number of stars in the universe is beyond comprehension. Counting stars in the Milky Way is only a first step, a glimpse of the immensity beyond, but it is a step that grounds us, reminding us that even one swirl of light contains more stars than we can truly imagine. For us on Earth, the act of looking up and counting has always been symbolic. It connects us to those who came before, who tried to tally the points of light by hand, who built catalogues and maps, who struggled with numbers too large for their time. It connects us to modern astronomers using satellites and computers to process billions of data points. And it connects us to the larger truth that our galaxy is immense, filled with suns, each with its own story, its own companions, its own possibilities. So when you look at the Milky Way stretched across the sky, remember what it represents. Billions of stars, each one a sun, each one distant, each one part of the great swirl of our galaxy. The light you see is the combined glow of countless lives of stars, born, burning, and dying across billions of years. It is a reminder that the universe is not empty, not sparse, but overflowing with light, and that even in just one swirl, one galaxy, the numbers already stretch far beyond our comprehension. After counting the billions of stars that swirl inside the Milky Way, it is natural to think of our galaxy as something immense in its own right, and it is. To cross it from one side to the other would take 100,000 years at the speed of light. Yet even that immensity is not the larger scale the universe offers. Galaxies are not isolated islands drifting alone in space. They gather, cluster, and weave together into structures far larger still. When astronomers first began to notice these patterns, they realized that the universe is not just a scattering of galaxies, but a vast web of connections with filaments, clusters, and superclusters stretching across billions of light years. The first hints came from the simple act of mapping. In the early 20th century, when astronomers began to recognize that the faint smudges in the sky were actually other galaxies, they started recording their positions. At first, the distribution seemed random. Galaxies appeared scattered like grains of sand thrown across a floor. But as the catalogues grew, patterns began to emerge. Galaxies were not evenly spread. They tended to appear in groups. Some were bound together in tight clusters, with dozens or hundreds of members. Others lined up in elongated chains connected by invisible threads of gravity. The more astronomers looked, the more they saw that the universe had structure on a scale far larger than any single galaxy. Our own Milky Way is part of such a group. It belongs to the local group, a small collection of more than 50 galaxies bound together by gravity. The largest members are the Milky Way and the Andromeda Galaxy, each with their own retinues of smaller satellites. The large and small Magellanic Clouds are 2 such companions of the Milky Way, visible from the southern hemisphere as faint smudges of light. These galaxies, though impressive on their own, are dwarfed by the scale of the group as a whole, which spans millions of light years. Beyond the local group lies an even larger structure, the Virgo Cluster, containing more than 1,000 galaxies. It sits about 65 million light-years away, and its gravity influences the motion of our local group, pulling us slowly toward it. The Virgo Cluster is only one of many such clusters, each one a massive congregation of galaxies, gas and dark matter. These clusters themselves are not isolated. They form part of even larger associations called superclusters, which can stretch hundreds of millions of light-years across. The most remarkable discovery of recent decades is that these clusters and superclusters are not randomly placed, but arranged in a vast cosmic web. galaxies trace out filaments that span across space like threads in a gigantic net. Between the filaments lie vast voids, regions tens or even hundreds of millions of light-years wide, almost empty of galaxies. The pattern is striking. A universe filled with structure, where matter gathers along threads and walls, leaving great bubbles of emptiness in between. This cosmic web was revealed through large surveys, like the Sloan Digital Sky Survey, which mapped the positions of millions of galaxies. When plotted in 3 dimensions, the distribution was unmistakable. Instead of random scatter, there were patterns of clustering filaments and walls. One of the most famous structures is the Sloan Great Wall, a filament of galaxies stretching more than 1 billion light-years in length. Another is the Laniakea supercluster, the structure that contains our local group, spanning more than 500 million light-years and including hundreds of thousands of galaxies. The name means immense heaven in Hawaiian, an apt description for something so vast. To appreciate the scale of these structures, imagine shrinking the Milky Way down to the size of a grain of sand. On that scale, the local group would be a cluster of a few dozen grains. The Virgo cluster would be a pile of thousands of grains spread across a table. The Laniakea supercluster would be a room filled with grains, hundreds of thousands of them, arranged in filaments and walls. And beyond that room would lie other rooms, other superclusters, all connected by the cosmic web. The universe is not a random collection of galaxies. It is an immense architecture shaped by gravity and the distribution of dark matter. The formation of this web began in the earliest moments of the universe. Tiny fluctuations in density after the Big Bang grew under the influence of gravity, pulling matter into filaments and clusters. Over billions of years, galaxies formed within those filaments, gathering in groups and clusters, leaving behind the great voids. The pattern we see today is a snapshot of a process still unfolding. Galaxies continue to move, clusters continue to merge, and the web continues to evolve. One of the striking aspects of the cosmic web is how little of it we can actually see. The stars and galaxies that shine make up only a small fraction of the universe's total mass and energy. Most of it is dark matter and dark energy, invisible to our eyes and instruments, detectable only through its gravitational effects. Dark matter forms the scaffolding of the web, a hidden framework on which galaxies are strung like beads. Without it, the universe would not have this structure. Counting galaxies is impressive, but realizing that they are only the luminous tips of a much larger invisible pattern is even more humbling. Clusters of galaxies themselves are extreme environments. Within them, galaxies orbit one another, sometimes colliding and merging. Hot gas fills the spaces between galaxies, heated to tens of millions of degrees, emitting X-rays detectable by telescopes. Dark matter halos surround them, extending far beyond the visible light. A single cluster can contain thousands of galaxies, trillions of stars, and masses equivalent to 1,000,000 billion suns. Standing inside one, if such a thing were possible, would mean living in a crowded sky, where galaxies fill the view in every direction, and yet between clusters the voids are almost empty. These regions, sometimes hundreds of millions of light-years across, contain only a few galaxies, scattered like lonely outposts. The contrast between dense clusters and empty voids gives the universe its texture, a balance between presence and absence, matter and emptiness. It is a pattern on the largest scale we know, larger even than individual superclusters, larger than the Sloan Great Wall. For us, inside one galaxy in a modest group on the edge of a supercluster, this scale is both humbling and awe-inspiring. It shows that our place in the universe is small, yet also connected to something immense. The Milky Way is not an isolated island. It is part of a filament, which is part of a cluster, which is part of a supercluster, which is part of the cosmic web stretching across the observable universe. Every direction we look, the pattern continues, filaments weaving into walls, walls enclosing voids, an endless network shaped by gravity and time. Measuring and understanding these structures has taken decades of effort. Each galaxy position mapped, each cluster identified, each redshift measured has added to the picture. The result is not just a collection of numbers, but a view of the universe as a whole, its architecture laid bare. It is a view that shows immensity in a new way. Not just large numbers, not just vast distances, but a pattern, a web, a structure that gives shape to the cosmos. And as immense as these structures are, they are still within the observable universe, still limited by the speed of light and the age of the cosmos. Beyond the horizon, the web may continue endlessly. We cannot see it, but we can imagine it. An infinite extension of the same pattern, repeating across scales we can barely begin to grasp. So when we think of clusters and superclusters, of filaments and voids, we are not just cataloguing objects. We are glimpsing the largest architecture in existence, the framework that contains everything we know. It is a scale that makes even the Milky Way seem small, a reminder that the universe is not just vast in distance, but vast in structure, woven together into a cosmic web that stretches beyond sight. When you think about how large the universe is, there comes a natural limit to what we can actually measure. Not because the cosmos itself stops, but because light can only travel so far in a finite amount of time. The age of the universe sets a boundary on how much of it is visible to us. We call that boundary the observable universe, and it is the farthest horizon we can ever see, no matter how powerful our telescopes become. It doesn't mark the edge of existence, only the edge of visibility. Beyond it, the universe continues, perhaps endlessly, but forever hidden from us. The concept begins with the age of the universe itself. By studying the expansion of space, astronomers estimate that the universe is about 13.8 billion years old. That means that the farthest light we can detect has had only 13.8 billion years to travel before reaching us. At first glance, you might think that sets the radius of the observable universe at 13.8 billion light years, but space has been expanding the whole time that light was travelling. As a result, the objects that emitted the most ancient light are now much farther away. Accounting for that expansion, the radius of the observable universe is about 46 billion light years. That makes its diameter roughly 93 billion light years across. That number is almost impossible to imagine. 93 billion light years. Each light year is nearly 10 trillion kilometers. Multiply that by 93 billion, and the figure becomes a string of digits longer than anything we can meaningfully hold in mind. It dwarfs galaxies, superclusters, and even the great cosmic web we've already discussed. The observable universe is the largest structure we can point to and say, with some certainty, this is what we can actually see. The contents of the observable universe are equally staggering. Current estimates suggest it contains around 2 trillion galaxies, each with hundreds of billions of stars. That means the total number of stars in the observable universe may be on the order of 1024, a 1 followed by 24 zeros. That is more stars than there are grains of sand on all the beaches of Earth combined. And each of those stars may have planets, moons, and systems of their own. The sheer abundance is overwhelming. The light we see from the farthest reaches doesn't come from individual stars or galaxies, but from the earlier state of the universe itself. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form, allowing light to travel freely for the first time. That light has been travelling ever since, stretched into microwaves by the expansion of space. Today, we detect it as the cosmic microwave background, a faint glow that fills the sky in every direction. It is the most ancient light we can see, a snapshot of the universe when it was less than 1 million years old. Beyond that, the universe was opaque, and no light can reach us from earlier times. The cosmic microwave background forms the ultimate limit of visibility. It is the farthest wall of the observable universe, the oldest signal available to us. By studying its tiny variations in temperature and density, astronomers have learned about the structure of the early universe, the seeds of galaxies, and the rate of cosmic expansion. It is like looking at the baby picture of the cosmos, frozen in time, stretched across the sky as a faint but all-encompassing glow. Within the observable universe, we see galaxies arranged in the same filaments and clusters as nearby, but stretched farther and farther into the distance. The farther away a galaxy is, the younger we see it, because its light left long ago. Some galaxies we see as they were billions of years ago, when the universe was much younger. The Hubble Deep Field, an image taken by the Hubble Space Telescope, revealed thousands of galaxies in a patch of sky no larger than a grain of sand held at arm's length. Each was at a different distance, a different age, together forming a window into cosmic history. Multiply that patch across the whole sky, and you begin to sense the immensity of what the observable universe contains. It's important to remember that observable does not mean actual limit. The universe likely continues far beyond the horizon we can see. It may be infinite, or it may curve back on itself, but we cannot know. The observable universe is like a bubble centered on us, defined not by what exists, but by what light has had time to reach us. Every observer in the universe has their own bubble, centered on themselves, and each sees a different slice of the whole. The true cosmos may be far larger, perhaps unimaginably so, but the observable part is the only one open to our eyes and instruments. The concept of the observable universe also changes how we think about our place in it. We often imagine ourselves as being in the center of the universe because the observable bubble is drawn around us. But that center is not special. Every galaxy, every observer sees themselves at the center of their own observable universe. The symmetry is complete. We are not privileged, only positioned within our own horizon of visibility. It is a humbling reminder that our perspective is limited, shaped by time, distance, and the speed of light. The expansion of the universe adds another layer. Galaxies farther away are receding faster, carried by the stretching of space itself. Beyond a certain distance, called the cosmic event horizon, galaxies are receding faster than light relative to us, making them forever unreachable, even in principle. Their light may still reach us if it was emitted in the past, but light emitted now will never arrive. That means the observable universe is not only a snapshot of what we can see, but also a record of what we can ever hope to communicate with. Many galaxies we see today are already beyond our reach, their current state hidden forever. This raises profound questions about what it means to know the universe. The observable horizon defines the limit of evidence, the outer wall of our empirical knowledge. Beyond it lies speculation. Perhaps the universe is infinite, repeating endlessly. Perhaps it is finite but unbounded, curving back on itself like the surface of a sphere. Perhaps there are other regions with different physical laws. We cannot say. All we can do is look as far as light allows, measure what arrives, and infer what lies beyond. The observable universe is both a window and a veil. For us, thinking about the observable universe is both humbling and comforting. Humbling, because it shows us how small we are, confined to one planet in one galaxy among trillions. Comforting, because it also shows us that we are part of something vast, something rich with structure and history. Every photon we catch from a distant galaxy is a message across billions of years, a reminder that the universe is connected across scales we can barely imagine. The observable universe is not just a boundary, it is a gift, the maximum slice of reality that we can access, filled with wonder at every scale. And so, when we talk about the size of the universe, what we really mean is the size of the observable universe, 93 billion light-years across, containing trillions of galaxies, filled with stars and planets beyond counting, ending at a wall of ancient light. Beyond that, we do not know. But even within that bubble, the immensity is overwhelming, enough to keep us wondering forever. When we speak of the observable universe, we're really talking about a horizon a boundary to what we can ever see. Just as standing on a beach lets you see only as far as the curve of the Earth allows, so too does the cosmos have a limit imposed not by curvature of the planet, but by the speed of light and the age of the universe. That limit is the cosmic horizon, the farthest distance from which light or any information could have reached us since the beginning of time. It defines the edge of the observable universe, and it explains why we cannot see farther, no matter how powerful our instruments may become. The fundamental reason lies in the finite age of the universe. If the cosmos has existed for 13.8 billion years, then light has had only 13.8 billion years to travel. It is as simple and as profound as that. Imagine standing in a vast dark room and lighting a candle. The glow spreads outward at a fixed speed. After 1 second, it has filled a small sphere around you. After an hour, a much larger sphere. After a day, larger still. The longer the candle burns, the farther its light can reach. In the same way, the universe has been lit since the moment it became transparent, and we are inside the expanding sphere of that light. The radius of the sphere is the cosmic horizon. Anything beyond it has not had enough time to send its light to us. But the situation is more complicated because space itself expands. Galaxies are not flying through pre-existing emptiness. Instead, the very fabric of space stretches, carrying them apart. This expansion means that the light we see from the farthest galaxies began its journey billions of years ago when those galaxies were much closer. Since then, space has stretched, so the galaxies are now much farther away than the distance the light travelled. This is why the cosmic horizon lies not at 13.8 billion light-years, but at about 46 billion light-years. It's the result of both the travel time of light and the growth of space along the way. One of the most striking aspects of the cosmic horizon is that it is not a fixed boundary in the sense of a wall. It is always changing. With each passing year, more distant light has time to reach us, so the horizon expands. New regions of the universe slowly come into view, but at the same time, because of cosmic expansion, some galaxies are receding so quickly that their light will never reach us, even in infinite time. This defines another kind of horizon, the event horizon of the universe, beyond which events can never influence us. Together, these horizons shape what we can see and what we can know. The reason we cannot see beyond the cosmic horizon is not because nothing is there. In fact, it is likely that the universe continues indefinitely, with more galaxies, more clusters, more filaments stretching endlessly. The horizon is simply the limit of what light has had time to show us. It's as if we're standing in the middle of a foggy field at dawn, with only the nearest hills visible. Beyond them, the landscape continues but hidden from sight. The cosmic horizon is our cosmic fog line, set not by mist but by time and physics. The earliest light we can see is the cosmic microwave background, released when the universe was about 380,000 years old. Before that, the cosmos was a dense hot plasma of particles and radiation, opaque to light. Photons could not travel freely, constantly scattering off electrons. It was only when atoms formed, trapping electrons in stable orbits, that the fog lifted and light was released. That moment is sometimes called the surface of last scattering, and it marks the visible boundary of the universe. Beyond it, the universe certainly existed, but its light is forever hidden from us. This is one of the deepest reasons we cannot see farther. The cosmos itself was not transparent until that moment. Astronomers use the cosmic microwave background as a kind of wallpaper of the universe, the farthest backdrop against which everything else is seen. Its faint glow, nearly uniform but with tiny fluctuations, tells us about the seeds of cosmic structure, the slight density differences that grew into galaxies and clusters. By studying it, we can infer what the universe was like before stars and galaxies formed, but no telescope will ever pierce past it in light. That horizon is absolute. Of course, other messengers exist besides light. Neutrinos, nearly massless particles that interact only weakly with matter, could in principle provide a window to even earlier times. Gravitational waves, ripples in space-time itself, may also carry information from epochs before the cosmic microwave background. In the future, detecting these signals could extend our horizon backward, not in space but in time. Still, for ordinary light, the cosmic horizon remains the ultimate boundary. The cosmic horizon also has implications for our understanding of the universe's size and shape. Because we can only see as far as the horizon, we cannot know whether the universe is finite or infinite. All we can say is that the observable part is finite, 93 billion light-years across. Beyond that, the universe could go on forever, or it could curve back on itself, or it could have regions with very different properties. The horizon hides the answer. It is both a boundary of vision and a boundary of certainty. Some people wonder whether future technology might let us see past the horizon. The answer is no, at least not with light. It is not a matter of building a better telescope. It is a matter of physics. Light from beyond the horizon has not had time to reach us. Until it does, it is as if it does not exist for us. The horizon is not like a curtain that can be pulled back. It is like the limit of a signal travelling at a fixed speed. Unless the universe suddenly becomes older overnight, the horizon will remain where it is. There is something deeply humbling about this. It means that no matter how far our science advances, no matter how large our telescopes become, we will always live inside a bubble of visibility. That bubble will grow with time, but it will always be finite. The universe beyond the horizon will remain forever hidden, reminding us that our knowledge, however vast, will always be limited. And yet, within that bubble, there is more than enough to study, more than enough to marvel at. Trillions of galaxies, countless stars and planets, cosmic structures of every scale, all visible within our horizon. The fact that we cannot see farther does not diminish what we can see. It also gives perspective on our place in time. If the universe had been younger, our horizon would be smaller. If it were older, our horizon would be larger. We live at a moment when the cosmos is 13.8 billion years old, and so our horizon is about 46 billion light-years. That number is not fixed in the cosmos. It is a reflection of when we are living. Future observers, billions of years from now, will see a different horizon. In that sense, the cosmic horizon is not just a boundary of space. It is a reminder that our vision is tied to a particular moment in cosmic history. When you stand under the night sky and look at the faint glow of distant galaxies, you are looking toward the horizon of the universe. Beyond them lies more, but invisible, unreachable for now. The stars you see are within our bubble, the galaxies too. But the cosmic web continues beyond, stretching farther than we can know. The horizon is not the edge of the universe. It is the edge of us, the edge of our knowledge, set by time, light, and the structure of space itself. And so, when we ask why we can't see farther, the answer is both simple and profound. Because the universe has a finite age. Because light travels at a finite speed. Because space itself expands. These are the rules that shape what we can know. They remind us that the cosmos is not ours to see in full, but only in part. Yet within that part lies more than enough wonder to last forever. The cosmic horizon is both a limit and a gift. The boundary of visibility, showing us the universe not as infinite, but as immense enough to stretch our imagination to its fullest. When people first looked at the stars, they imagined the universe as static, fixed, eternal. The heavens seemed steady and unchanging, a backdrop against which the dramas of life unfolded. Even when telescopes revealed new details and galaxies were recognized as vast systems of stars beyond our own, the assumption remained that the universe itself was stable. It was only in the 20th century that a remarkable truth began to emerge, one that would reshape our understanding of everything. The universe is not standing still. It is expanding. Space itself is stretching, carrying galaxies away from one another, growing as we watch. The discovery came from careful observation. Astronomers noticed that light from distant galaxies was shifted toward the red end of the spectrum. This redshift meant the galaxies were moving away from us. The more distant the galaxy, the greater the redshift, and the faster it seemed to recede. In 1929, Edwin Hubble published the results that confirmed this relationship. The universe was expanding. What seemed at first like a surprising result has since become one of the cornerstones of cosmology. It's important to understand what this expansion means. The galaxies themselves are not flying through space like projectiles. Rather, space itself is stretching, and the galaxies are carried along with it. Imagine dots drawn on a balloon. As the balloon inflates, the dots move apart, not because they are moving on their own, but because the surface beneath them is expanding. The universe works in a similar way. The galaxies are like the dots, the fabric of space, the balloon. As space grows, so does the distance between galaxies. This has profound consequences for how we think about size. It means that the observable universe is not a fixed container, but a dynamic one. The galaxies we see today are much farther away than they were when their light began travelling toward us. The ancient photons we catch in our telescopes have been stretched by the expansion of space, their wavelengths elongated, their energy reduced. This is why the light from the earliest universe arrives as microwaves rather than visible light. The cosmic microwave background stretched across billions of years of expansion. The rate of expansion is measured by what we call the Hubble constant. It tells us how fast galaxies recede per unit of distance. For every million parsecs, roughly 3.226 million light-years, galaxies recede at a measurable speed. The exact value of the constant has been a subject of ongoing debate, with different methods giving slightly different results, but the principle remains. The farther away something is, the faster it appears to move away. This relationship defines the growing fabric of the universe. What's most striking is that the expansion is not slowing down, as one might expect from gravity pulling everything together. In the late 1990s, observations of distant supernovae revealed that the expansion is actually accelerating. Something, dubbed dark energy, is driving galaxies apart more and more quickly as time goes on. This discovery added a new layer to the mystery. Not only is the universe expanding, but the rate of expansion is increasing, reshaping the future of the cosmos in ways that are still being explored. For us, this expansion is invisible in daily life. The scale of the solar system, even the scale of galaxies, is not changing in any noticeable way, because gravity holds them together. The space between Earth and the Sun, between the stars of the Milky Way, remains stable. Expansion becomes meaningful only on the larger scales, between galaxies separated by tens or hundreds of millions of light years. It is only there that the stretching of space overwhelms local gravity, pulling galaxies apart, carrying them along in the flow of cosmic growth. The idea that the universe is expanding also changes how we think about the past. If everything is moving apart now, then at some point in the past everything must have been closer together. Extrapolating backward leads to the concept of the Big Bang, the moment when the universe was compressed into a hot, dense state and began to expand. This was not an explosion into space, but the expansion of space itself from an earlier, smaller state. The galaxies, clusters, and structures we see today grew out of that expansion, seeded by tiny fluctuations in the early universe. The cosmos as we know it is a history of growth. It also changes how we think about the future. If the expansion continues to accelerate, galaxies will drift farther and farther apart. Over billions of years, distant galaxies will move beyond our cosmic horizon, disappearing from view as their light can no longer reach us. The night sky, billions of years from now, may look emptier, with only the local group of galaxies remaining visible. The cosmic web itself will fade into isolation, each cluster becoming a lonely island in an expanding sea. The universe is growing, but with growth comes separation, and the future may hold a cosmos more solitary than the one we see today. The concept of an expanding universe is not just a matter of observation but of daily perspective. It reminds us that nothing is static, not even the largest scales. The universe is alive with motion, not in the sense of galaxies travelling like ships across water, but in the deeper sense of the water itself rising, stretching, and carrying them along. Every photon of ancient light we receive is shaped by this expansion, stretched in its journey, marked by the growth of space. Every measurement of distance is really a measurement of growth. Even the language of size is altered by expansion. When we say a galaxy is billions of light years away, we have to specify whether we mean the distance when the light was emitted, the distance the light travelled, or the distance now after expansion. All three are different. The simple act of defining distance in an expanding universe becomes a lesson in the dynamic nature of reality. The numbers are not fixed, but change with time, reflecting the stretching of the cosmos. This expansion also ties back to why we have a cosmic horizon at all. If the universe was static, light from infinitely far away would eventually reach us, and the sky would be infinitely bright. The fact that it is dark at night, what's known as Olber's paradox, is explained by the finite age of the universe and its expansion. There has not been enough time for light from all regions to reach us, and the stretching of space dims the light that does arrive. The night sky is not only dark because stars are far away, but because the universe itself is expanding. And so, when we talk about the size of the universe, we cannot separate it from this growth. The universe is not a box containing galaxies, but a fabric that stretches and carries them apart. It is growing not into anything, not into a larger space, but into itself, creating new space as it expands. This is a difficult concept, but it is the reality revealed by observation. The universe grows, and we are inside that growth, carried along like passengers on a balloon that never stops inflating. The expanding universe is perhaps the most profound answer to the question of size. It tells us that there is no fixed scale, no static number that defines the cosmos. The size of the observable universe grows with time, horizons shift, galaxies recede. The universe is not just vast, it is becoming vaster with every passing moment. We live inside something that is not only immense but dynamic, a cosmos that grows as we watch. Once you've accepted the immensity of the observable universe, with its trillions of galaxies stretched across 93 billion light-years, the natural instinct might be to stop there. After all, the numbers are already overwhelming, the structure's already more than the mind can hold. Yet in science, one question always seems to lead to another. If the observable universe is only a slice of the whole, what lies beyond it? And if the cosmos we see is not the only one, could there be even more? Other universes, other realities, a multiverse of possibilities extending past the horizon of what we can observe? The idea of a multiverse is not simple speculation pulled from imagination, though it certainly inspires imaginative thinking. It arises from the very physics that describes our universe, from the theories that attempt to explain why space expands, why the cosmic background exists, and why the laws of nature appear as they do. To explore whether there could be more, we begin with the simplest form of the question: is the universe infinite? If the cosmos extends beyond the observable horizon without end, then by definition there are regions we will never see, no matter how much time passes. They exist, they evolve, they contain galaxies and stars just as ours does, but they are forever cut off from us by distance and expansion. In that sense, even an infinite single universe functions as a multiverse of sorts, with countless regions never in contact. The galaxies we see are only a drop in an ocean that continues endlessly. That possibility alone is staggering. But theories of cosmic inflation go further. Inflation is the idea that, in the first fractions of a second after the Big Bang, the universe expanded exponentially far faster than it does today. This rapid inflation smoothed and stretched space, explaining why the cosmic microwave background is so uniform and why the universe appears flat on large scales. The mathematics of inflation also suggest that it may not have happened just once. In some models, inflation is eternal, producing bubble universes like pockets of foam in a boiling pot. Our universe could be one bubble, our observable cosmos one expanding region, while countless others exist elsewhere, each beyond reach. If that is true, then the multiverse is not just larger than our universe. It is an endless sea of universes, each with its own version of physics. Some may have the same constants and laws as ours. Others may differ slightly, with stars that burn differently, with chemistry that unfolds in unfamiliar ways. Still others may differ so much that no galaxies, no stars, no life could ever form. In this picture, our universe is one realization among infinite possibilities, a single variation in a vast cosmic lottery. Another perspective on the multiverse comes from quantum mechanics. In the quantum world, particles exist in multiple states until measured, collapsing into one outcome. One interpretation, called the many worlds interpretation, suggests that all possible outcomes actually occur, each in its own branching universe. Every time a quantum event happens, the universe splits, producing parallel realities that diverge from one another. If true, this would mean the multiverse is not just vast in space, but branching in possibility, with countless versions of reality unfolding alongside our own. String theory, an attempt to unify the forces of physics, also hints at a multiverse. Its equations allow for many possible vacuum states, each corresponding to a different set of physical laws. The landscape of solutions could represent countless universes, each with different values for fundamental constants. In this framework, our universe is one valley in a vast landscape, not special in itself, only one possibility realized among many. For us, standing on Earth and looking at the stars, these ideas can feel impossibly abstract. It is hard enough to grasp the size of our own universe, let alone to imagine countless others. Yet the questions arise naturally from the physics we use to describe reality. Inflation predicts it. Quantum theory suggests it. String theory allows it. The multiverse is not proof, but possibility, a frontier of thought where the limits of observation meet the implications of mathematics. One challenge with the multiverse is that it may never be directly testable. By definition, other universes lie beyond our horizon, inaccessible to light, unreachable by signals. Some argue that this makes the idea unscientific, because it cannot be falsified. Others point out that if the theories that predict it are correct, then the multiverse is a logical consequence, whether or not we can observe it. The debate continues, balancing the desire for evidence with the recognition that some truths may be forever beyond measurement. Still, there are hints that might someday give us indirect evidence. Collisions between bubble universes, if they happened, might leave imprints in the cosmic microwave background. Subtle patterns in the distribution of galaxies might reflect physics from outside our bubble. Quantum mechanics continues to provoke experiments that probe the foundations of reality, and string theory seeks ways to connect its landscape to observable phenomena. The multiverse remains speculative but not arbitrary. It is rooted in the effort to understand why the universe we see has the properties it does. For us, thinking about the multiverse is an exercise in humility. If the observable universe already contains trillions of galaxies, each with billions of stars, then adding countless other universes on top of that makes our place smaller still. Yet it also expands the sense of possibility. If reality is a multiverse, then anything not forbidden by physics may exist somewhere. Worlds like ours, worlds utterly unlike ours, histories that diverge from our own, all unfolding in parallel or scattered across infinite expanses. The multiverse is both overwhelming and strangely comforting. It suggests that reality is richer than we can imagine, larger than we can ever see. it also reshapes how we think about uniqueness. Our sun feels special to us, yet it is one of hundreds of billions in the Milky Way. Our galaxy feels immense, yet it is one of trillions in the observable universe. Our universe feels vast, yet it may be one of countless others in a multiverse. At each step, what once seemed unique becomes one among many, and the scale expands again. This pattern humbles us, but it also connects us to something far greater than ourselves. Whether or not the multiverse exists, the very act of considering it stretches our imagination. It forces us to confront the limits of knowledge, to ask whether reality is confined to what we can see, or whether it extends infinitely beyond. It blurs the line between science and philosophy, between observation and speculation. It invites us to think of reality not as a single universe, but as a vast possibility space, a grander whole in which our universe is a single part. The multiverse may remain forever beyond direct sight, but it is a natural extension of what we know, a horizon of thought beyond the horizon of observation. Whether infinite in space, branching in possibility, or varied in laws, it represents the ultimate expansion of scale, the idea that the universe is not the universe at all, but one piece of something larger still. After wandering outward through distances so vast they defy imagination, it is natural to pause and look back at ourselves. We have spoken of galaxies stretching across 100,000 light-years, superclusters spanning hundreds of millions, and a universe nearly 100 billion light-years across in its observable extent. We have even entertained the possibility that our entire universe is just one bubble among countless others. Against such immensity, what is a human being? A body less than 2 meters tall, a lifespan of less than a century, a presence confined to a thin atmosphere wrapped around a small planet. By every measure of size and scale, we are almost nothing at all. And yet here we are, tiny observers in a boundless sea, asking questions about the whole. The contrast is almost absurd. On one side, numbers so large that they spill beyond comprehension, distances measured in trillions of kilometers, times measured in billions of years. On the other side, a single heartbeat, a single breath, a single human life. It might seem as though one side cancels out the other, that our smallness erases our significance. But that is not the way to see it. Our smallness is part of the wonder, part of what makes the act of asking about the universe so extraordinary. Think about what it means for a mind, built of cells and chemicals, to imagine galaxies and cosmic webs. Those cells are themselves the products of stars, formed from elements forged in the cores of ancient suns. The iron in your blood, the calcium in your bones, the carbon in your cells, all of it was born in stars that lived and died billions of years ago. In that sense, you're not separate from the universe, but made of it. You're the cosmos turned inward, contemplating itself. The human scale may be small, but it is deeply connected to the larger whole. On Earth, we tend to measure scale by what we can touch and see. A mountain feels enormous, a forest feels vast, an ocean feels endless. Yet compared to the Earth itself, even the highest peak is a minor bump, the ocean a thin film. Compared to the solar system, the Earth is a dot. Compared to the galaxy, the solar system is a mote of dust. And yet, from this dot, from this mote, we can look outward and trace the patterns of galaxies. Our reach is not in physical size, but in thought. The human mind is small in dimension, but immense in curiosity, capable of spanning the gulf between atoms and the cosmos. The human scale is also a reminder of perspective. To us, a kilometre is a long walk, 100 kilometres a long drive, 1,000 kilometres a long flight. These are the units of daily life. They shape our sense of distance and time. To a planet, these numbers are trivial. To a star, they are negligible. To a galaxy, they are invisible. And yet, for us, they are everything. The human scale is the scale at which life is lived. at which moments are felt, at which meaning is made. That is why the vastness of the universe does not erase us. It frames us. It gives us context. Our smallness does not make us insignificant. It makes our existence remarkable. In a universe filled with billions of galaxies, life has emerged here on this one world with the capacity to wonder. That capacity is not diminished by scale. It is highlighted by it. We are small, and yet we are aware of the vastness. We are tiny, and yet we reach with our minds across billions of light years. The human scale also reminds us that our tools extend our senses. We cannot see galaxies with our eyes alone, but we build telescopes that can. We cannot travel to distant stars, but we build equations that predict their motions. We cannot touch the cosmic microwave background, but we build detectors that measure its faint glow. In this way, our small bodies do not confine us. Through science, through curiosity, through imagination, we extend ourselves outward, expanding our reach far beyond our physical limits. And yet, for all our extensions, we remain tied to our scale. We eat meals measured in grams, walk distances measured in steps, live lives measured in decades. The universe does not conform to those measures. It offers us numbers too large, times too long, spaces too vast. To bridge that gap, we invent units like the light year, metaphors like balloons and grains of sand, stories that help us grasp what cannot be directly held. These are not just conveniences, they are bridges between the human scale and the cosmic scale, between our smallness and the universe's immensity. Some people feel dwarfed by the universe, even frightened by it. They look at the night sky and feel their lives made meaningless by comparison. But another way to see it is as an invitation. The universe is not diminished by your smallness, nor are you diminished by its vastness. You are part of the same whole, a participant in the same story. Your life may be short in cosmic terms, but it is long enough to wonder, long enough to connect, long enough to share in the immensity. The boundless sea of the cosmos does not erase the drop of water that is you. It gives the drop its place, its shimmer, its moment of reflection. It is also worth remembering that on the human scale we are not alone. Just as galaxies gather into clusters, people gather into societies. Just as stars orbit in galaxies, we orbit in families, in communities, in cultures. We are part of systems both small and large, nested within each other, each giving meaning to the other. The human scale is not only about the individual body or mind, it is about the network of lives and relationships that make up our experience. That too is part of the boundless sea. When you sit quietly and think about the universe, you're not stepping outside the human scale. You're expanding it. You're taking the time to stretch your imagination beyond the horizon of daily life, and in doing so, you're enlarging what it means to be human. That act of stretching is what allows us to connect our smallness to the universe's vastness. It is what allows us to feel at home in a cosmos that could otherwise feel overwhelming. The human scale is tiny, yes, but it is also rich. Within a span of less than a century, a person can learn, love, create, share, and pass on knowledge. Within the confines of a small planet, humanity has built telescopes that reach back to the dawn of time, probes that have touched the outer edges of the sun's reach, instruments that have measured the faint glow of the earliest light. These are not the acts of an insignificant species. They are the acts of a small but determined one, capable of connecting its scale to the largest scales imaginable. So when we think about the human scale in relation to the cosmos, the lesson is not despair but perspective. We are tiny observers, yes, but we are observers nonetheless. The universe is vast, but it is also knowable, and we are part of it. Our smallness is not a flaw, it is a feature, a reminder that meaning does not depend on size, that wonder does not require immensity, that even in the boundless sea of the cosmos, a single human life can be filled with connection to the whole. After all the distances we've travelled in thought, From the smallness of Earth to the vastness of galaxies and beyond, the mind eventually seeks rest. It's a journey of expansion, step by step, until the numbers and scales reach heights where words falter. The observable universe stretches nearly 100 billion light-years across, and perhaps beyond that lies a multiverse, endless and unknowable. Against such immensity, our own place is small, and yet in that smallness there is something deeply human, something grounding. The act of looking outward is also an act of turning inward. Every measure of distance, every description of galaxies, every thought about horizons and expansion eventually circles back to the quiet fact that we are here, breathing, listening, reflecting. There's a kind of whisper that runs through all of this. Not a literal sound, but the quiet message carried by the cosmos itself. A message that says, you are part of this. The atoms of your body were forged in stars. The thoughts you think are powered by the same physics that governs galaxies. The universe is not separate from you. You are woven into it, as much a part of the infinite as the galaxies and clusters that stretch across the night sky. That whisper is always there, hidden behind the noise of daily life, waiting for quiet moments when you can finally hear it. When you lie down at night, looking up at the stars or simply imagining them behind the ceiling, the scales we've spoken of might drift through your mind. A light year, a galaxy, a supercluster, an observable universe. Each term carries weight, but it is not the weight of burden. It is the weight of perspective. It says the world you know is part of something immeasurable, and yet here you are, able to sense it. That is no small thing. To exist, to perceive, to wonder, that is enough to connect you to the infinite. The whisper of the infinite is not loud because it does not need to be. It is present in the faint light of stars that left their galaxies millions of years ago and now arrive as gentle points in the night sky. It is present in the glow of the cosmic microwave background, the oldest light we can see, stretched into waves so soft they pass unnoticed around you every second. It is present in your own heartbeat, a rhythm sustained by elements that were once part of exploding suns. All of these are threads in the same fabric, reminders that the infinite is not far away but here, all around and within you. What is most soothing is that the universe does not demand anything from you. It simply is. It expands whether or not we measure it. It forms stars and galaxies whether or not we name them. It carries on, vast and patient, without judgment or expectation. In that sense, the infinite is comforting. It tells us that whatever our worries, whatever our struggles, they are small in the face of cosmic time. Not small in a way that erases them, but small in a way that puts them in perspective. Like waves on the surface of an endless sea, they rise and fall, but the sea remains. And so the journey outward becomes also a journey inward toward rest. The infinite does not need to be solved tonight. It does not need to be held in the mind all at once. It can simply be felt, like the soft weight of a blanket, like the slow rhythm of breathing, like the quiet hum of thought winding down. The infinite is vast enough to carry every question, and quiet enough to let every thought dissolve into calm. As you drift, you might imagine yourself floating among the stars, carried gently along the arms of the Milky Way, past clusters of galaxies, past the filaments of the cosmic web. You might imagine the horizon of the observable universe, glowing faintly with the light of the earliest time, not as a wall, but as a reminder of how far light can travel. And beyond it, you might imagine silence, not empty, but full of possibility. A silence so deep it feels like rest itself. That is the whisper of the infinite, soothing and unending. Here, in this moment, you are both tiny and vast. Tiny in that your body is small, your lifetime brief. Vast in that your mind stretches across billions of years, across light years of distance, across ideas of universes beyond universes. You are the meeting point of small and large, of fleeting and eternal. That balance is what makes the whisper of the infinite so steady, so calming. It speaks in both directions at once, reminding you that you are small enough to rest and vast enough to belong. And as your eyes grow heavy, you can let go of the numbers, the scales, the distances. You can let the galaxies fade, the clusters dissolve, the horizons blur. You can let the universe hold its own immensity while you return to your own small scale, your own breathing, your own presence. The infinite does not need you to keep it in mind. It will remain steady and patient while you rest. All you need to carry with you is the quiet whisper that you are part of it, and that being part of it is enough. The stars will still shine while you sleep. The galaxies will still turn. The universe will still expand. And you will still belong, woven into it, a tiny observer in a boundless sea, held by the same laws that guide the infinite. That whisper will remain gentle and unending, a reminder from the cosmos that you're both nothing and everything at once. And with that thought, you can let go, carried softly into rest, as if the infinite itself were lulling you to sleep. And so, we arrive at the quiet end of our journey. From the smallness of home to the reaches of galaxies and beyond, we've wandered through distances so immense they dissolve into calm. The universe will keep on expanding, stars will keep on shining, galaxies will keep on turning, whether we are watching or not. For now, all you need to do is rest. Thank you for joining me on this exploration, and for letting curiosity guide you gently towards sleep. If you found comfort here, I invite you to return again, whenever you'd like to drift through science at a softer pace. You can also support this space by subscribing, so that more nights and more journeys can follow. For now though, you can let go of the numbers, let go of the distances, and let the vastness of the cosmos hold you like a blanket of stars. Breathe slowly and let the whisper of the infinite carry you into dreams. Good night.